right, good afternoon, everybody. Thanks for joining us today to our second annual CAIML Symposium. For those of us who join us for the first time, I see some new faces here. Let me start with a few words about CAIML and our purpose, our mission. We have been in existence for 1.5 years now. So this is our second symposium, and we are an interdisciplinary, interfaculty center here at TU Wien. And our purpose, our mission is to connect researchers and students here at TU Wien who are interested in artificial intelligence, in machine learning, and also in the ramifications of these topics. We like to say that there are 3 pillars that make up the center, and you can see them here. The first is artificial intelligence. So here we understand symbolic methods, logics, that's a big part of it. The second pillar is machine learning, which are more like continuous methods or different approaches. And we believe that this is important to bring together researchers that have different backgrounds, right, who are experts in different methods. And hopefully the sum will be better than the part. The third point you see here is about the ramifications of artificial intelligence, and we are very happy and proud to have a strong community here in digital humanism in Vienna, which is a philosophical subfield, if you will, that concerns itself with the ramifications of our work onto society, onto future. And we believe this is really important because we are in a very fortunate, lucky position that our work is really important to what people do, and it has a very good chance to shape the future for the betterment of humans and society. So those are the 3 pillars, and you see here the 12 board members that comprise our center. So we got together, right, it's a bottom-up approach, and we have here 12 board members from all areas of artificial intelligence, and I'm sure many of you will know at least some of them. So at this point, I would also like to mention the summer school that we organize beginning of July. And big shout out to Stefan, that was his initiative, and he put lots of work into organizing it. So we are very much looking forward to it. We have a cast of 10 distinguished speakers beginning of July. So if you have not heard about it, please go to our website, caiml.org, and you will find all the details there. The program is already up. We are also very happy to announce our industrial sponsor, our first one, Palfinger. So you can see the logo here. Of course, you know that Palfinger is a mainstay of Austrian industry and also a worldwide market leader. So we are very happy to have them on board here. And yeah, we expect that there will be more sponsors forthcoming. All right, so much about our center. Let's have a quick look at the program. We'll start with 2 welcome addresses. And we are proud and honored to have Gerti Kappel here, the Dean of the Department of Informatics / Computer Science here at TU Wien. And also Michael Stampfer, head of the Vienna Science and Technology Fund, who has been supporting artificial intelligence and machine learning also by their funding programs. So we are very happy to have you both here. We'll continue with a talk by Shawe-Taylor. So if you've been working in machine learning, probably you have already stumbled the name. So more about him later. Then we'll continue with a talk by Casilli. After the coffee break starts at 3:15, we'll reconvene here at 4 p.m. and we'll continue with a talk by Wolfgang Nejdl. As you can see here from the topic, we've tried to choose 1 talk for each of the 3 pillars that we just mentioned. So we hope that we have a diverse program here that will appeal to many of you. And we'll close it off with a panel discussion moderated by Julia Neidhardt. Again here, the names you already saw, Casilli, Gerti Kappel, Wolfgang Nejdl and Shawe-Taylor, and we are very proud to also have us joining for the panel discussion Helga Nowotny, former president of the ERC. All right, so without much further ado, I would like to ask you, Gerti, for your welcome address.
Good afternoon, ladies and gentlemen. First and foremost, I would really like to thank Stefan Woltran and Clemens Heitzinger for putting up this really important program and talking about, and there's not a title, but I tell you the title, and talking about the secret ingredients of improving AI. When I have heard the title, Secret Ingredients, immediately hidden figures came into my mind. It's all about people. It's all about marginalized groups. Who have been the hidden figures? They have been the colored women, exceptional mathematicians who helped USA in the 50s and in the 60s to win the race for the space. And they haven't been known, I think, until only recently. It was President Barack Obama who gave the Medal of Freedom to one of the three most prominent of these colored women, of this brilliant mathematician. And then there was the book, Hidden Figures, and also the film. And if you don't know the movie, I can really advise you look at the movie. So I guess we will hear more about these secret ingredients. But there's a second part to the title, the secret ingredients for improving AI. Now we could ask, what does it mean, improving AI? Improving it in the way for what we use it. And I think the symposium couldn't be more timely. It's just a couple of days ago that Geoffrey Hinton, one of the Turing Award awardees 2018 for machine learning, was stepping back from his job at Google because he wants to be more outspoken, to be more, I would say, constructive, critical about what we do with AI and how we use it. And again, there's a pattern. And there's the pattern of that famous scientists who develop something and all of a sudden it becomes kind of autonomous what they have developed. And the pattern is Joseph Weizenbaum, who did ELIZA in '68. It was, I think, a more or less simple basic program, building up a kind of an interaction between a machine and a person, and the person thought it is a kind of a psychology behind the wall. And Joseph Weizenbaum was very kind of astonished and negative kind of touched how his invention all of a sudden was thought that it will change the world and that people are not necessary anymore. And I think we have a similar situation now where we have to really think of what does it mean to use symbolic and sub-symbolic AI, also called machine learning. How can we apply it in the different applications so for the good of the mankind, for societal good? And I guess there is a big kind of bandwidth. On the one hand, we have the lethal autonomous weapon systems, and on the other hand, we have Stone Age. And I guess we don't go back to Stone Age, but we also don't want the automatic weapon systems. And everything in between, it's in fact up to us. There is more to improving AI, the secret ingredients of improving AI. It's also technical-wise. What does it mean to develop these systems? What does it mean in terms of sustainability? We all know that on the one hand, AI is used for developing a sustainable world, but at the same time, it's using a lot of energy. And it was just in this issue, in the May 2023 issue of the CACM, that there is an article about, please tell your compute that not only we should provide the software and we should provide the data when we publish our work, we should also talk about how much energy are our systems using? And how can they compare with others? And how can we improve it? And last but not least, improving AI means we can't do it alone. It's inherently an interdisciplinary topic, as already Clemens mentioned it. We have to take into account legal issues. We have to take into account societal issues, economic issues, ecological issues. So all ESGs you can imagine, everything is part of the usage of AI. But why are we discussing it at a technical university? Is it really our task to think in these terms? Yes, it is, because we develop the systems. We can decide if we have privacy by design, security by design, or even digital humanism by design. So there is no excuse. We are at the forefront of development, and I'm very happy that you are all here, and I wish you a very exciting afternoon. Thank you.
Thank you, everybody, and welcome also from my side. I also had an idea about the secret ingredients of AI being people. As you, Gerti Kappel, talked about the pioneers, I had to immediately think of the hundreds of thousands of people, real people who are sitting somewhere, mostly in some windowless shacks or wherever over the world, annotating for AI for $1 an hour, or being the censor for AI-based or based platforms that they don't run totally out of control. So these are also secret ingredients which should be at least in our thoughts with us for 1 second. Which leads me to, I'm never preparing for such, which might be a big fault of myself, never preparing for such short intro sections, which leads me to my proposal for a motto for today, which is coming from the German Romantic movement, or on the brink between classicism and the Romantic movement. It's the wonderful saying, der Menschheit Würde ist in eure Hand gegeben, which is a Schiller poem, so the dignity of humanity is put into your hands. And I want to elaborate for 1 minute on that in various directions. First of all, that's true, yeah. As you said, we are depending on what you do with the secret and not so secret ingredients, yeah. We could have a nicer world, but what most of you computer scientists propose to us as the immediately appearing nicer world through your fabulous problem-solving facilities is not very convincing to many of the rest of us. I will not go into detail to that, but don't be too sure that your fixes to all the world problems. I know there are no Elon Musk sitting in this room, that's for sure, but I think some of this, we can fix all the problems thinking is here in all kinds of engineer education curricula. So don't be too sure that you can fix mankind's problems. Second is that you have you need a global approach in your doings, and that leads me to a second work of art, which is also called Der Menschheit Würde ist in eure Hand gegeben, which is a sketch from the post-war area by a cabaret star. Some of you will remember Helmut Qualtinger, where Helmut Qualtinger, speaking like that, he's unsuccessful light opera actor with a speaking problem, and he and his colleague are sitting somewhere and making all the misfortunes of the last decades wonderfully. So I had one said I played the fourth dwarf in Snow White and the Seven Dwarfs. The other said I played the fifth dwarf. How did you play it? Yeah, hintergründig. So and that's the local way to play things. And the whole sketch ends with a kind of sigh. In Linz müsste man sein. So that's also what I would like to leave here. It's no matter whether we are in Linz or in Vienna, we are playing on a global field, and we should play that game professionally, which needs a lot of input, where Linz is a little in the advantage, but a lot also of professional communication, where Linz is not in the advantage at the moment. So with global ambitions, that's about science and technological advances, but also, and I don't have, as one of the apostles of digital humanism, I don't have to bring it here because most of us are feeling the same. It's also about a global discourse and the global level of linking technological and engineering approaches with social science and humanities approaches. And you can link it, can make intelligent global contributions if you have your strong local examples. So today, tomorrow, and the day after, we will have to find projects to do that. You will have the opportunity, as the Vienna Science and Technology Fund will next week issue 2 funding programs for digital humanism, where also AI and machine learning researchers will be very welcome. So that's a short spoiler. But we have done it already in the last year. I didn't count, but around 3 million a year, 2 to 3 million a year of the WWTF funding, which is 15 to 20%, 15% of our funding goes into AI and ML project every year, in some year more, like this year where we have a large funding call which is called AI and ML for biology and medicine. So we care, we should care even more. Der Menschheit Würde ist in eure Hand gegeben, bewahret sie, is then again not quoting but Schiller. Thank you very much.
Right, thank you very much to both of you for your welcome addresses. Now let's have a look at the program. So we have 3 talks by distinguished researchers, distinguished speakers. The first of which will be by Shawe-Taylor, and it's my task to introduce you. Shawe-Taylor is a professor at UCL, University College London. His main research areas are statistical learning theory, but he has also contributed to neural networks, machine learning, and graph theory. He obtained his PhD in mathematics at Royal Holloway, University of London in '86. And he also completed a Master of Science in the Foundations of Advanced Information Technology at Imperial College. He was promoted to Professor of Computing Science in '96. In 2003, he moved to the University of Southampton to lead the ISIS research group, ISIS research group. He was appointed director of the Center for Computational Statistics and Machine Learning at University College London in 2006. And subsequently, he became head of the Department of Computer Science, also at University College London, a position that he held till 2019. He has also been very active in community service, meaning heading large research projects. So he coordinated a number of EU projects on the theory and also practice of machine learning, including the NeuroCult project. So you might know him from there. and he's currently coordinating. He coordinated a network of excellence in pattern analysis, statistical modeling, and computational learning involving 57 partners. So lots of community service. Recently, in 2018, he became also UNESCO Chair of Artificial Intelligence, and he's also heading the leading trustee of a UK charity, the Knowledge for All Foundation. He's a really distinguished researcher, having published more than 300 papers, which have been cited an incredible 92,000 times. I'm very much looking forward to his talk. So he will talk about Bayesian learning, right? It's part of it, and also PEC-Bayes, probably approximately correct estimates combining a Bayes approach. And he's also well known for his work in support vector machines and deep learning. So I'm very much looking forward to it. So please, John, the floor is yours.
Thank you so much for such a generous introduction and for the invitation to be here. It's a great privilege and honor to be part of this event, and also to in such a fantastic environment, apart from the rain, but we'll live with that. So let me just try and see if I could work out how to do this. There you go, perfect. So my secret ingredient is really to try to, in a sense, talk about if we want to improve AI, I think it would be a good start to try to understand AI and how it works. And I think there's quite a significant gap between the incredible performance we're seeing in some of the recent developments in AI and our basic understanding of the core science that lies behind that. And I think there's even, I might go as far as to say, a desire to sort of not dig too deeply, to kind of become a believer, if you know what I mean. I mean, in the sense of, it works, why should we question it? It's fantastic, you know, let's move forward. The future is bright, the future is orange, or whatever it is. But I think that is a very dangerous position to take, because until we understand a technology, the danger of using it loosely is even greater. And I think we've seen that happen to some extent in the way AI has been used, and some of the consequences are quite scary, particularly in terms of their influence on humans and the idea of the information bubble that has been created by feeding people content that engages them for whatever reason and don't ask the reason. This is the kind of application that I think applied in a naive way can have very dangerous consequences. But my talk won't concentrate, I'm afraid, on that. I'm going to go into a much more technical side of trying to understand the basics of why a system that is trained with some finite data actually performs so well on unseen new data. That, for me, is the core question, in a sense, of understanding AI. However, I think the secret ingredient that is also talked about here is understanding what these systems that are able to mimic our intelligence are telling us about ourselves. And this is a more philosophical question that the Digital Humanism Center, I think, is attempting to address. And I think it's a fantastic area and a fantastic opportunity, in the sense that the fact that AI is making these significant advances is unlocking some of the capabilities that we have, is also forcing us to reevaluate what it is to be human and what actually distinguishes us from artificial systems. And whereas I think for many, many years we saw ourselves as the intelligent animal, the one who had the brain, who could solve interesting problems, that's now perhaps being called into question. I don't know if you saw the film on AlphaGo, but I would recommend it again. I also recommend the film, but the AlphaGo film has a very interesting sort of duality to it. On the one hand, there's the team developing AlphaGo, and there are a lot of computer scientists and I happen to know some of them. But on the other side, there is actually the Go players who become involved in both the development and, of course, in actually playing against AlphaGo itself. And they are people with a deep tradition of thinking about what it means to play Go. It's almost a religion for them, I would say. And for them, it is completely unthinkable that a machine could in any way capture that level of depth of understanding, insight, etc., that they have. And through the film, they come to realize that actually it does, and it's actually going to defeat them. And their reaction to that and how they deal with that is absolutely fascinating. I think it's a very, very insightfully constructed film in that respect. And I actually went to the opening, and the person who made the film said that that wasn't his intention at the beginning, but his intention was just to document the actual computer scientists preparing this thing. But as he saw and the interaction with the Go players themselves, that became a whole new aspect of the film. And I think it really is giving us the kind of insights that are pointing the direction in which we should be thinking about digital humanism, or what it is to be a human being in this new context where AI systems are assuming so much of the capabilities that we took to be, if you like, unique to humans. However, coming back to what I'm going to talk about, which is very much more technical, I think one of the core things we want to understand, and not just assume in some sense, AI systems are doing magic. They're not doing magic. Proposition number one. They are in some way implementing a system of learning that is able to capture incredibly complex structures and capabilities that we would not have expected. And so why? What is happening? How is that possible? And I think I'm certainly got an answer to that. But what I think I would like to propose, as a sort of leitmotif of what I want to present, is that we do need to think very broadly and much more creatively in a way, in order to try to break that through to a better understanding of that learning process. And I believe through doing that, we will actually also improve our ability to apply that technology in a much wider range of applications and to scale up. Maybe you may say GPT is already scaled up enough, but scale up in a way that is more effective in the use of also resources. The cost of training GPT was alluded to, but I think with a better understanding of the technology, we could actually train systems with similar power with far less compute resource. So with that, I'll dive in, and I just want to, as I say, emphasize from the frame of this is that if we want to understand learning, learning is really about generalizing. Learning is always about taking some finite set of data, trying to infer from that finite set of data some underlying principle, and the ability to which, or the extent to which we do that, will be evident in the degree to which that system will then generalize to new data that it has not seen before. So this is a very simple kind of example of this, where there are two classes of blue and red, and we might try to learn to separate them. And there may be some noise actually in the data, so that if we try to fit every data point correctly, we end up with the wiggly line, which is clearly not capturing the real underlying structure, whereas the the more likely correct line is the nice curved line, which, albeit makes some mistakes on the training data, but is much more likely to generalize well to test points. So we learn from examples about an underlying phenomenon, and we don't want to just memorize the data we've seen. That would be known as overfitting. We want to generalize and perform well on unseen data. So statistical learning theory was mentioned as one of my kind of research interests. And I think it's been something that has come very much from a computer science background. Most traditional, I'll mention this again a bit in a minute, but most traditional statistical view has been around expectations of performance. Statistical learning theory is about high confidence. And the idea is that you want to look at the whole distribution of errors you might get from a learning algorithm when applied to a certain problem. And the distribution is over the different training sets that you might get. So think about training sets as being generated by some random process. Somebody's gone out, done some measurements, and they might have done them in a different machine or a different context, et cetera, et cetera. So you might get many different training sets, but they're all measuring the same phenomenon. Now, what we want to have is an algorithm that will perform well on any training set. We don't want to have the situation where it might perform well on a training set or might not, because we in the real world will only be having one training set to work from. And so you don't want to be in the situation where your training set ends up with a very bad result, or there's a good chance it will end up with a very bad result. You want to be confident that it will be good, whatever the training set that you get. So we don't want to focus on the mean of this error distribution over training sets. We want to be confident that on the single sample that we will have from the particular measurements that are collected and annotated by those guys in that dark room without any light, that will actually be well spent work and will deliver a result that will be good. So statistical learning theory is looking at the tail of the distribution and finding bounds and then translating those into algorithms that will guarantee that performance with high probability. And it's over, as I said, the random samples, or training samples, which we'll consider to be of fixed size m. So it's similar to a statistical test in the sense that you would normally in a statistical test have a confidence level, which would be the chances that the conclusion of the test was not being true are less than 1%. The chances that the data could have generated that particular output would be less than 1%, and then you reject the null hypothesis. In that sense, we're looking in a similar way at this idea that the chances that this performance that we're observing was by chance is less than 1%. We're at that level, let's say, of the tail of the distribution. And this leads to the acronym that was mentioned, probably approximately correct, which doesn't sound very confidence-inspiring, but what it means is there's a confidence parameter which is telling us the probability that we could have been misled by the training data. And we're saying with high probability, given the training data, this one training sample we got, with high confidence, we're going to be approximately correct in the sense that there will be some bound on the error that we will observe on our test data. So this is the high confidence result that we would like to see from statistical learning theory, and then derive algorithms that implement that. Now here it is in a diagram in which this is the density graph of the performances we get from different training sets. Okay, so we've run a training algorithm with different training sets, actually done for a particular task of breast cancer analysis of breast cancer cell images. And the idea is that you've run the algorithm many times with different random samples, you've observed the test error on each of those, and you plot a histogram of those errors. And what I've looked at is two algorithms. One is a support vector machine, which I will show has this property that it optimizes the performance in this sense of the tail of the distribution, and a more naive algorithm, just a Parson window estimator. And you can see that if we look at the 95% confidence point, this is with the same sample size, the same function class in this case, is completely fair comparison. The support vector machine is able to bring that bound on the performance to a much tighter maybe 0.27 or something compared to the Parson window. This was a fairly small sample size. But if you look at the means of the distributions, they're very comparable. There's almost no difference between them. So this is just to kind of illustrate the performance that we're aiming for. So I'll skip fairly quickly through just a little bit of notation just to get the ideas behind what we're, the analysis. So we're thinking about a learning algorithm mapping from a training set of size M, which is a sequence of pairs, input-output pairs, inputs taken from a set X and outputs from a set Y. And we're using some hypothesis class of predictors, so the algorithm will, from that training set, identify an appropriate function from that class. As I said, the training set is just a set of input-output examples, and we're assuming that those samples are generated IID, independently and identically distributed, from some unknown data-generating distribution. So this is the sort of the real world generating that data. We don't need to make any assumptions about that distribution for this analysis. So that is the power of the analysis, is in the generality in terms of the distribution generating the data. The key assumption is this IID assumption that the data is generated independently and identically, which is not always actually true in practice. In many cases it's not. There are weakenings of that assumption, but to some extent the way the analysis works is typically to try to bring back to this IID assumption. So I'll leave it there. If there are questions, obviously I can comment on that later. So what to achieve from the sample? So what we want to do is to learn a predictor, but also to have some certification of the predictor's performance. And so the idea then is that if we have that certification, we can use that to drive the algorithm. So we drive the algorithm to optimize the certificate of performance, and that's exactly what the support vector machine does. And of course, it needs to be informed by some prior knowledge resulting from some principle of inductive bias. And this is the thing that really, I think, needs to be drilled into in terms of understanding the performance, because there's no free lunch in the sense that if we have a totally general system, then it cannot learn. If there's any function is possible and equally likely, then whatever amount of data you give the system, it won't be able to learn. It has to have an inductive bias. And this really comes back to the question, okay, so what is the inductive bias implicit in a deep learning architecture that is actually enabling it to perform so well? Those are the key questions that people somehow are not asking. So the certification of performance is in terms of what happens beyond the training set, and we will quantify that in terms of what we call generalization bounds. And as I mentioned, these two goals interact. The better you have a certificate, you can inform your learning algorithm with that certificate. So we normally measure performance in terms of a loss function, which is how well we do on a test point. So given, or on the training data, in this case, this in-sample risk is the training performance, which is the average loss on the training set. And then the out-of-sample theoretical risk is the performance on a randomly drawn test point, or on a random estimation of that on a test set. And the loss can be either a classification 0-1 loss, or a regression square loss, or a relaxation of the classification, so-called hinge loss, or indeed a log loss if we're talking about just fitting a distribution density estimation. So just quickly setting the scene in terms of what I want to really mainly focus on is this link that was mentioned between Bayesian analysis and pack learning that I've already mentioned, that I think is a very nice way of linking an intuitive understanding of how we might put in a prior or inductive bias into an algorithm, and this more formal analysis of the performance. But the more traditional way of thinking about this was just in terms of a set of hypotheses. And for a single hypothesis, we can just apply a very simple, straightforward bound of this type, which is Hufting's basically bound turned around to give a high confidence probability greater than 1 minus delta. The test performance on this hypothesis will be less than or equal to the in-sample performance of this hypothesis plus a correction term, which is just the likelihood of us having a deviation between the training and test. And then we can just use a union bound over a finite sample of hypotheses to actually apply this same bound to each of the mod H, or the size of H, which I've just put in here in this way. That's just the size of that set. And just taking a delta divided by that number, substituting it in and applying the bound that number of times, and we end up with this bound. And you can see immediately that what's happening is we're kind of getting an influence of the complexity of the function class in the bound. So the more functions we have, the weaker the bound comes on the performance of the test point. And this is sort of, if you like, I just mentioned this, we can actually put a probability distribution over the functions in the class, a prior distribution, which is sort of has this pack-based flavor, and we get a bound, a somewhat similar bound, but now instead of the size, the individual bound on hypothesis HI depends on the prior probability we actually put on that particular hypothesis. So again, it's the same union bound, except it's a weighted union where the PIs weight the different functions. And so for each individual function, we get a different weighting. And so the tightness will depend on the different function that we get. But immediately we get this flavor, which has become folklore around statistical learning theory, that somehow the function class size or complexity is influencing our bound very critically. And of course, that is, an immediately bad situation to be in if you're thinking about deep learning with the hugely complex function classes, because the bounds, any bound you place a priori on the power of that function class will be way, way, way too flexible in order for a bound of this type to give any significant bound on performance. And this is partly where this idea of magic has come from. Okay, the bounds can't tell us anything. We're into magic territory where it's working incredibly well. And this would be true certainly for so-called VC, Vatnik-Chervonenkis dimension, which deals with uncountably infinite function classes, or Rademacher complexity, although that can make some in performance bounds for support vector machines, which are potentially also infinitely VC dimension, but certainly would not tackle the deep learning systems that we have. And part of what I want to do is to show today that actually you can get statistical learning theory type bounds for these very complex function classes through this pack-based approach. So the difference that happens with pack-based is that we now consider distributions over hypotheses rather than just a set of hypotheses. So we have, remember, we've got already distributions over examples. So we're now going to be a little bit sort of confusing and introduce distributions over functions as well. And that's the Bayesian approach. So Bayesians would have, I'll mention again, but they would have a prior distribution over the functions, and then based on the data that is observed, they would update that to get a posterior distribution over the functions. So this is now going to, these two types of distributions are going to interact. So you've got two distributions over functions and a distribution over the examples. Can get a bit confusing. Okay, so the way you would work, normally you would have a prior distribution, which has to be set ahead of seeing any examples. Now, in the case of, I'll come to it, but in the case of Bayesian learning, this would somehow be the true prior. In PAC-Bayes framework, we don't have to have that belief in it being true necessarily. It just has to be fixed before you see the data. And then based on the data and knowledge of the prior, you would create a posterior distribution over the function class, which is somehow moved towards being good on the data that you've observed. And the predictions in the PAC-Bayes framework, and this isn't the same necessarily as the Bayesian, classical Bayesian, you draw a function from your posterior. When you get a test point, you draw a function from your posterior distribution and use it to classify that or map that test point. So each prediction gets a fresh random draw. That would not be the case in a typical Bayesian framework. So the way we analyze this is to extend those error estimates for individual functions to now error estimates for distributions, which are just taking that prediction methodology and translating it into the expectation of the error. So now the error is over a random draw of the function h, the expected value of the error. This is in the training set, and this is in the test set. And furthermore, we're going to see enter this CAIML divergence between the posterior and prior distributions, and that is just the expectation over the posterior distribution of the log of the ratio of the probabilities of the function. Okay, so how does this map with more traditional Bayes? So in traditional Bayesian inference, you would have a prior distribution, okay, but the mapping from prior to posterior is based on the statistical likelihood, so it would typically be a fixed mapping based on updating that prior distribution based on the likelihood that the particular function could have generated that particular error pattern on the data that you've observed. So they're literally just updating that probability to a posterior. In the PAC-Bayes, and this prior, as I mentioned before, is in some way capturing some true state of the world or true state of the likelihood of the particular set of functions. Obviously that's quite hard to do. So typically what you actually do is pick some convenient prior that is possibly easier to work with. But in some sense, the correctness of the analysis is conditional to some extent on the correctness of this being the correct prior. So it sort of undermines that slightly. Okay, in the PAC-Bayes framework, it doesn't really matter whether this is the correct distribution or not. It is a distribution. It can be chosen whatever way you want. It can be chosen conveniently or inconveniently. And again, the posterior distribution is not dependent on, you can choose whatever distribution you want. But of course, what you're going to try to do is, given these two distributions, there will be a bound on the test performance. And what you'll be doing is choosing that distribution to optimize that performance. So the distribution will be kind of inspired by, the bound that is given. The bound holds whether these, however you choose these two distributions, the bound holds. So if you choose a bad prior, you just get a weak bound. Okay, it's not so good. But the better you choose your distribution, but of course you must do it before you see your training date, so you can't cheat, is going to make, but of course, I'll show you examples where you choose part of the data to choose a prior. So that gives you a very good prior, and then use the rest of the data in order to choose the posterior and evaluate the bound. So the bound is still correct in this case. So the prior can be seen as your kind of exploration mechanism for the set of hypotheses, and the posterior is the way you update that based on the data that you've actually seen. So In the PAC-Bayes framework, you have to fix the distribution before you see the data, update, choose a, oh, sorry, I've gone the wrong way. There we go. So, yeah, I think I've said all this. This is just about highlighting the difference. The only thing perhaps to add here is this data distribution, which, again, in the Bayes framework typically is only concerned with the randomness in the actual output. So the inputs are not part of the distribution that's considered in terms of the data for the Bayes distribution, for the Bayes, analysis. But the randomness is in the noise model, which is used to then update the probability of the functions. But in the PAC-Bayes, it's the input distribution that I described, generating the input and output in the training sample. So the IID distribution that we've discussed. Okay, so here's the generalized PAC-Bayes theorem. And again, I'm not going to, hopefully, I think we're going to be too short on time to go into too much detail. But what I wanted to highlight is the interaction of several points here. The first thing to point out here is that this, on the left-hand side, is some divergence, let's call it, some measure of discrepancy between the in-sample performance of our posterior distribution Q and our out-of-sample performance of our distribution Q. And this is bounded, this divergence between these two quantities is bounded by, so these are two probabilities. Probability of error that we make on the sample, which of course we can estimate and we know, and the actual generalization error that we're going to observe on a randomly generated test point. So we're interested in bounding actually this quantity here, the out, R out of Q. That's the performance of our methodology once we've fixed Q. And what we're saying is that this will be close to the in-sample, where close is defined by this right-hand side here. So the right-hand side, the key, this is a relatively, potentially quite small constant. We'll look at it in certain, so ignore this for the moment. And the delta was this confidence parameter. I thought the probability of, 1 minus delta of this being correct. So delta is the probability that this bound fails to be true by chance because of we're unlucky on the sample, but it's under the log. So it's going to be relatively benign dependence on delta. Therefore, the key property here is this KL divergence between the prior and posterior. So what is this telling us? If we want a good performance bound on the test performance, we want to make sure that we don't shift too far from the prior distribution, but we want to shift far enough in order for this training sample performance to be small. So if we can have something pretty close to the prior that performs well on the training sample, then we'll have a tight bound on the test error. Okay? So that's the sort of take-home message. This is this quantity that I mentioned. I won't go into it in detail, but it can be bounded to be small in many applications, but it's clearly depends on the application. So again, I won't go into too much detail because I think I'm going rather slowly. So where are we with time? Yeah, very slowly. So I will skip very happy to share the slides so people can have a look at it. But I think the main take-home message of this general theorem is that it's actually not that hard to prove. Okay, so it's basically a change of measure inequality here that brings in this KL divergence, where you look at this this quantity here for some function phi of h. Phi of h is going to be, in our case, this quantity here, delta of k over m comma r. Sorry, going the wrong way again. So this is a relatively straightforward. We then apply Markov's inequality, very straightforward. And we observe some, so basically we then put these together in a sequence of this type. So this is the quantity we're trying to bound. We use Jensen's inequality to move the expectation out through delta. Delta was chosen to be a convex function. And then apply the change of measure inequality, and then use Markov's inequality, and finally expectation swap, and this is where we use the actual IID of the sample in order to do that expectation swap. And then there's just this binomial law and supremium over the risk, and we have the result. Okay, so let's say the main sort of take-home point is this isn't actually very, very deep mathematics. It's really quite straightforward, and from it we can derive many of the very standard results of Pack-Bayes theory, for example, Langford and Seeger, where the delta is just chosen to be this so-called small KL, which is just treat these two as binomial distributions with these probabilities, KL divergence between those binomial distributions, and we get plug that in, and we can get this bound. This is McAllister's bound, which is also applicable for regression. Catoni's bound, which is a slightly different take, and then there's one by Alquier et al. Okay, I'm going to skip this, which is just a bound on that, the derivation of the bound on this thing that I said was a small constant in the case of a classification. It turns out to be just 2 root m, it was under the log, so it's relatively benign. And again, I don't want to spend too much time. Okay, so now I'm going to talk about applying this in the case of SVMs, but my main aim is to get on to showing you some results for deep learning systems. But I just wanted to highlight that this can be applied very straightforwardly to motivate SVMs and obtain very tight bounds. So the prior here is taken to be Gaussian at the origin. This is all in the kernel-defined feature space. And then the posterior is taken in the direction of the learned weight vector of the SVM. And there's a scaling parameter to optimize the bound. We can choose any posterior distribution, so we can choose this scaling parameter to optimize the bound. And then there's the posterior distribution. And this is the bound that results. And this is just a straight application. In fact, this is slightly weaker because this should be a root 2m here rather than an m+1, but that's a slightly older version. And we can evaluate these in the case of an SVM. This is the stochastic performance of the true performance of the stochastic classifier on the test data. We can upper bound the performance of the deterministic in this case of the SVM because of the fact that it's a linear classifier with a symmetrical distribution, and so we actually get a bound that is on the fixed, SVM performance, which is twice this stochastic error. And this is the empirical performance. Again, we can estimate that because the posterior distribution is also a Gaussian, and we can just apply that to actually evaluate exactly what the stochastic error is on the training set. Again, it turns out to be a function of the margin. Again, I won't go into the detail, but it's very easy to estimate. And the KL divergence between two Gaussians is, again, a very simple function. It's just that scaling parameter squared, mu squared divided by 2. So these are the confidence parameter. And so we end up with this as our bound on the SVM. Probability of misclassification of now the fixed SVM weight vector is less than or equal to that twice that came in from moving from stochastic to deterministic. The minimum over this scaling parameter of I'm calling it the KL inverse, but it's this is the left-hand side of that bound, and this is the empirical error. Sorry, this is the left-hand side, the right-hand side of the bound, and this is the empirical error that I said we can estimate. So just plugging those in gives an exact bound on the performance. And we can see that it is a motivation for the SVM, except that we've moved from the hinge loss of the SVM, which we need to make the thing convex, to this loss function, which is the loss function that actually comes out of the SVM bound. But this is an upper bound, so we can use it in this sense. So I think, again, we can explore improving the prior to improve the performance, and again, bounds that depend between the prior and the posterior. So again, this was this idea of using part of the training data to get a better prior distribution rather than taking that prior distribution at the origin. And we can even improve things a little bit further using that, and indeed motivate some better algorithms potentially. So here's the prior now in terms of a weight vector learned on part of the training data, and then your full training data to learn the posterior direction. And this is now hopefully a smaller KL divergence between the two. And this is the, again, bounds that you get depending on that. So I'm going to skip forward now to just give you some examples of performance. And this is on the UCI, so simple data sets, but just to give you an indication of how things work. And using tenfold cross-validation to do model selection and comparing that with doing model selection using the bounds. And we can see that the Pack-Bayes, this is the simple Pack-Bayes bound, can often do, the TE is the test error, can mimic the quality of twofold or even tenfold cross-validation. On average, it actually does slightly, this is an average over these training sets, it actually does slightly better than using cross-validation. This is the prior pack, which actually doesn't do so well in terms of model selection, but interestingly, typically gets quite good bounds. If we use the more complex algorithms that I skipped over in terms of actually optimizing the SVM based on this prior, then we can get even tighter bounds in many cases. So these bounds typically are all tighter than the one we got with the pack naive, the most straightforward application of the Pack-Bayes scenario. So we get very, very tight bounds, but actually the model selection doesn't, well, in this case, it doesn't do as well as this pack. It does beat tenfold cross-validation in this case, but not by as much. So the take-home story is that these bounds are very competitive. They're, within something like a factor 3 or 4 of the true test performance. So we're certainly getting something that is, let's say, giving a reasonable understanding of what's going on. But they're not always optimal for model selection. But they certainly are competitive. Okay, so how much more time do I have? 5 minutes? 5 to 10 minutes. Okay, I'm going to really just mention this distribution defined prior. So but I won't spend more than just a mention here because I want to get on to the deep learning stuff. There's an idea that actually we don't ever need to know the prior distribution. We only need to be able to compute the KL divergence between prior and posterior. So Catoni had this idea of actually defining the prior distribution in terms of the true risk, and then the posterior in terms of the empirical risk, which of course we can then evaluate. And there is now a technique to compute a KL divergence between these two. So it gives us a way of almost cheating the odds in that we actually use a very good prior distribution that we don't know how to compute. And yet we can compute it posterior. So it's a very attractive option. Unfortunately, it doesn't work out so well in practice because the bound on the KL is not always tight. This KL, you can bound it, but it's not a very tight bound. And the tightness depends on the situation that you're in. And so it's not very informative for actually giving you insight into the performance. So although it's a very attractive option, and we've looked at various variants of it, we derived an update on this bound and so on. I'm going to skip over it because I think it's not. It relates to also stability, which was something that Bousquet and Elisiev did early on and we can improve their bounds, but it's not actually giving really good performance. So what about performance of deep neural networks? So this is sort of, in a sense, something that was held out as intractable for statistical learning theory because of the complexity of the function hypothesis classes. And so the question was, are we able to capture something about this model that is able to inform type bounds? Now, to some extent, we've done that with support vector machines. So in the sense that support vector machines, if you use, say, a Gaussian kernel, are a very, very complex function class. They are able to approximate, in principle, any function. And the thing that informs the tightness of the bound is this margin that we measure and optimize. And the idea is the margin is telling us that actually we're not using that full complexity that we might need in some cases. We're using a much simpler subset of functions, if you like, that is actually able to approximate, in this particular case, the target function. And so is there something similar we can do with deep neural networks? So the idea is that if the deep network solution has a wide basin of good performance, then perhaps the pack-Bayes bound, because our posterior distribution can be a lot looser, we can have a much broader posterior distribution, is that able to reduce the KL divergence term, which is where all of the complexity is encoded in that pack-Bayes bound, the dimension of that KL divergence term is the number of weights in the network. But if their movement that we actually make is so small in many of those weights, and that the overlap of the distributions is so high, actually we won't pay such a high cost. So this was also proposed by Gerti and Roy, and they derived some of the tightest bounds by training to expand the basis of attraction, and hence not measuring good generalization of normal training. So they've also tried actually to look at this work that I mentioned on the prior distribution defined in terms of the data generating distribution. So we've updated those experiments and extended them, and the idea is we optimize the pack-Bayes bound, and we look at a number of different options. One is the classic, the quad, which is in terms of estimating the KL in terms of a quadratic function, and what we're calling the F lambda bound, which was the Catoni bound, or the FBBB, which is more Bayesian. Now, this is some kind of evidence that we are matching true performance. So this is a risk certificate versus the actual performance. And we're seeing there is a good correlation between the two. And so we're actually confident that we're able to do some model selection, potentially, using these performance. So we've done some experiments with quite complex CNNs and fully connected networks. And we've applied it to both MNIST and CFAR data, so reasonably large. MNIST isn't, but CFAR is reasonably large training data. So this is the type of performance that we're getting. Now, there are a number of points on this that are worth. So these are the different algorithms. This is if we use random initialization. This is where if we use a learned prior function. This is the fully connected network. And this is the risk certificate that we get. And this is the stochastic predictor. So for example, this F quad on the learnt prior, we've got a certificate that's telling us our 0-1 error is 0.0279, and the actual 0-1 error is 0.0202. So we're within striking distance. The deterministic is lower, and remember, we're bounding the stochastic error. So this is the thing we're bounding. Actually, the true error turns out to be lower, We don't have a bound on this directly because of the fact that we don't have that property that it's a linear function and that the distribution is symmetric. So we don't actually have that. We only have the performance bound on this. So what I'm trying to evidence is that these bounds are capturing clearly something about the learned performance, but what they fail to do is capture the performance of the ERM. So if we actually continue to train with a standard, empirical risk minimization and apply the bounds to in other words, we don't directly run the algorithm to optimize the bounds, then the performance of the bounds is very, very weak. So it's something that we are able to inform an algorithm that will optimize the bounds, and that clearly shows that we're capturing a property of these systems that is actually we're able to reproduce, but the systems are performing well in cases that we can't analyze. And so clearly we're not capturing all of the performance that we should be in order to fully understand what's going on. So these are with the CFAR data, just the more complex data. Again, similar kind of results here, for example, learnt on 70% the prior, 0.25 is our risk certificate, 0.21 is the actual performance. So again, very, very tight. And if we even increase the number of layers up to 15 layers, so reasonably complex networks, again, the risk certificate is 0.21, the actual performance 0.16, and in this case 0.18 and 0.1463. So again, very tight performance. So I'll finish now, but just to mention, this framework has been applied much more generally beyond SVMs and supervised learning, but also for regression and other classification and different types of application, density estimation, reinforcement learning, sequential learning, and so on. So I just wanted to, indicate there are many references here that might be of interest. But the focus has been on the key question of learning being generalization. And modern machine learning appears in some cases to contradict many of the conclusions of statistical learning theory. But with this refined analysis, one's able to actually uncover at least partly the performance, explain partly the performance of these very highly parameterized systems. But I think there's still many, many questions that remain unanswered. So I'll finish there. Thank you.
Thank you very much. Are there any questions? We do have a microphone here. Any questions?
Thanks for the talk, John. That was a lot, so I'm not sure I fully followed, but my question directly was, what do you think, or can you tell me a bit more about the implications for things like AutoML that way? Because when it's about model selection, right, this whole area of machine learning that tries to simply optimize what the best model might be. So how do you see the application in this direction here?
Well, I mean, so I think we've done, we haven't done enough to evidence, but from the experiments that I had, certainly in terms of the, if I go back to that plot there, I mean, basically AutoML is attempting to do these things without, and what we potentially have here is a system that can learn, to identify its performance on the fly rather than having to do a whole cross-validation in order to, which is clearly quite expensive. So in principle, this should be a speed up for AutoML, but I think there are quite a few, steps to make that a reality. And the problem I have, in a way, is the point I was making at the end there, that we have to make the algorithm optimize the bound, which is fine, but we're also getting very good performance without optimizing the bound, which doesn't seem to be explainable by the bound. Now, it's possible, so the question is, do those systems that learn make broad local minima? We're just not able to detect them because they're sort of skewed in some way because this is axis parallel, and essentially all of the optimization of the bound is just rotating the distribution, the posterior distribution, in a way that aligns with the so it's possible that's the case, but we don't know. And I think that would be very interesting in order to try to understand, is this really what's going on in deep learning performance? It could be that it is, but the jury's out still on that. Okay.
Thanks.
Hello, thank you for the talk. I think my question is actually, or your answer to the previous question is sort of related to my question already. I was just interested in the counterintuitive behavior of optimizing for a bound, but actually achieving worse test error with the SVMs, as you showed on this table.
Yeah, so exactly that is counterintuitive, and that just proves to me we're not capturing all of the performance in some sense. So we're over-optimizing for something, but and of course what the performance we get is consistent with the bound still, but we've somehow with the other methodology we've actually kept something else that the bounds are not explaining, so the actual performance is better. I don't have a clear understanding of why that is, and we've tried quite a few things, so it's the jury's still out, I think, is the answer. I mean, sorry, I should just say, maybe I didn't mention this, but when I started out on bounds, a factor of 1 million between the performance and the actual test bound was good, So to get down to a factor of, 1.3 is pretty good, It feels good. It's disappointing that it's not actually translating into a reliable mechanism for model selection. That's disappointing.
Yeah, I mean, I wasn't actually that interested in a factor between them or the scale between them, just the relationship where it seems like you optimize for one, but then the other one appears to be worse.
That's the problem. They aren't always the same distance between them.
Yeah.
So you optimize for one, and you actually get something that's not so good as if you optimize, maybe differently. Yeah. I mean, the same is true in some sense for cross-validation. And cross-validation is a bit of a. I mean, there's not even a bound associated with cross-validation. It's just a heuristic. So we shouldn't be putting it up on a pedestal. It's just the methodology people tend to use. Yeah.
Any further questions? If not, then please, those of a seat next to each other available, defragment the space, because we have more people out there waiting to be seated. So just squeeze together to the empty seats, and in the meantime, we will set it up.
All right, if there are no more questions, let's ask John again. Sit it, John.
You don't need power for your...
Hopefully not. Okay. This will push me to be brief, because power will eventually run out. Okay. I'm sorry, yes.
Is it? Yeah, now that's better. That's definitely
That's definitely better than before. Hi, my name is Peter Knees. I'm heading the special interest group on digital humanism in CAIML. And I have the pleasure to introduce or host this talk by Antonio Casilli. Antonio is a professor of sociology at Télécom Paris. He's also a researcher at an interdisciplinary institute of innovation, which is part of the CNRS. He deals in his research with digital communication, fundamental rights, the future of work, which is very related to what he's going to talk about today. And then he's also the co-founder of the digital platform Labor and the International Network on Digital Labor. And then I realized why I was asked to give this introduction here, because people thought, hey, Peter doesn't speak French, so let's have him introduce all these things here. So he's
all the titles in.
No, but he's the author of the book En attendant le robot.
Waiting for Robots. It's coming out in English in a few months.
Awesome. That would have been better for doing that. Yeah. Well, anyway. And he was also editorial advisor for a French television documentary called Invisible les travailleurs du clic.
Yes.
Right.
Invisibles, click workers. That is about hidden figures, as Gerti was saying.
Exactly. I mean, to me, it could be like the new fragrance by Dior as well as it is. But apparently, it's just a new incarnation of like sweatshops, which is like, you see the connection here between the fragrance? Okay. Anyway, but also to mention, he's a guest professor currently at the TU Wien Informatics Doctoral School. And so this talk is also part of the current trends in computer science. Of the lecture series here in current trends in computer science. So without much further ado, thanks for being here, Antonio, and looking forward to it.
Thank you, Peter. Thank you. And now for something completely different. I am supposedly the sociological cherry on the top, of this afternoon. And my task is to, lead you through a long history of human computing. The title that I gave to this presentation is A Contra-History of AI, but it could have been also a contra-history of ML. In some settings, this would be blasphemy. I understand that here it's something of an obvious thing to say. Nevertheless, it's not obvious what I'm going to introduce to some of you. Some others already are familiar with this matter, because I want to talk about the long history of the human contribution to machine learning. Gerti Kappel at the beginning already mentioned this very US-based story of the hidden figures that helped NASA and other governmental agencies during the 20th century to calculate some of the most important endeavors in human scientific breakthrough. But this story is also a very Austrian and Vienna-based story. I would like to start with this. This is my setup in my office at TU Wien. Nothing fancy, apart probably the coffee. As you see, I am asking ChatGPT to provide me with a timeline for this presentation. Don't worry, I won't use it, it's scrap. But importantly, Vienna is an important place for the development of one history of computing in general. If we go back to the 1950s, of course, there is this computer that was developed here that was called at the time Maybreeze, which is my Fürnen? Löften. Thank you very much. My German is defective. And if we go back even further in time, we are confronted with this splendid and luxurious calculating machine built by Anton Braun in 1727 and presented to the emperor. Now, this is one story. The title of this presentation is A Counter-History, meaning providing an alternative timeline, an alternative genealogy, as Michel Foucault would have said, and this leads us to an entirely different set of facts. For instance, one might say that my setup here in Vienna is also the result of other historical processes that revolve around the production of data. Like this is something that nobody here in this room is old enough to have known. This is the ancestor of the pocket calculator, the electronic and mechanic pocket calculator. This is a ready reckoner, which this is a thumb size one, a small booklet containing pre-calculated entities. And that was extremely useful to convert weights and measures or to calculate prices, and that was really used. And this is somehow the democratic version of the scientific antecedent to this, which are, of course, all the tables, mathematical tables, nautical tables, tables for calculation of errors and deviation or surveys and economic entities that have been produced widely, since a few centuries, let's say. We will focus on what in history we call modern history, basically 18th century to today. And it is important to highlight the fact that this is related to what we do here and to what we live here as users of technology, because this technology here is, of course, the result of this history, the mechanical one, but also of the data-based one. Now, as you can see, there is a gap between the history and the counter-history, and we need to fill that gap, because otherwise the counter-history will sound like a conspiracy theory, and I'm not into that. The important point to take into account here is that today we have probably a skewed perception of what's going on in machine learning, especially on the commercial side of it, because we are constantly confronted with PR operations that highlight the technical and algorithmic and computational and hardware side of it, meaning that whenever there is a new GPT out, and now it's like the Beaujolais Nouveau, it's like the new wine of the year, you have it every year, you are also facing a barrage of media stories that tell you that now there are 100 trillion parameters, and of course this is also related to, better models, bigger models, and better performances and bigger computational power. This bigger and more performative, more performing aspect is, yes, important, but we do not have to forget that all the breakthroughs in our discipline, I include myself into AI, ML, because I've been studying it for several years from my point of view, of course, is that every time we have had a breakthrough, this breakthrough has been preceded by the production of huge amounts of data. Let's take, for instance, the 1997 IBM Deep Blue versus Kasparov win, when the first time a computer was capable of beating a chess champion. This was preceded a few years before that by the publication of 25 million matches, meaning matches of chess, in the extended book of chess and the game dataset that was also published after that. The IBM Watson performance by winning the television quiz Jeopardy was preceded by the publication of 8.9 million Wikipedia tables, to say nothing about AlphaGo, and I'm probably less enthusiastic about everything related to AlphaGo in general. But anyways, whenever we have a big breakthrough, there is always somewhere the production of huge amounts of data. Let me give you quickly the example of GPT-4. I understand that you are entirely familiar with this, but GPT-4 is not only now several trillion parameters. We don't know exactly how many, although the estimates is probably 1 trillion, then 100 trillions. But anyways, it has been preceded by the publication in 2012 to 2016 of the data that are on the platform Common Crawl, which provide, of course, with an entire snapshot of what's going on in several places of the web. Now, Machine learning is also a lot of data, and the lot of data, and this is the basic assumption for the rest of my presentation, is also a lot of human in the loop, or humans in the loop in this case, because it's always plural, and by plural I mean several 100 million plural. According to an estimate by our colleagues at Oxford Internet Institute, there are now 165 million people performing this kind of job. What kind of job? Well, you have probably seen in the media this story soon after the launch of ChatGPT. It was discovered that several hundred persons were working in Kenya, and now they have created a union to protect their rights. These are the hidden figures, or probably the heirs of the hidden figures of the 1950s and 60s. But I can tell you that there's definitely more than that. Let me give you some glimpses of the kind of fieldwork activity, which is collection of data, empirical data from a sociological point of view. What I do is I travel the world and I observe people working on data, on your data usually, and they do it from very diverse settings. I think at the beginning was Michael was mentioning, yes, the rooms without windows. Yeah, there is a window, but it's closed. It's in a small room of two teenage boys that have created this very, very small operation, 5 persons, all friends from the neighborhood in an African country, and they have, shifts, and they work 24 hours, 7 days a week, but performing microtasks on microtasking platforms. In other cases, we have encountered very standard operations. This looks like any company in any open space in any country. Again, it's in the global south, or majority world, as I prefer to call it. And in other cases, we have encountered very, let's say, informal ways of working. People working from cyber cafes. This is in Antananarivo, in the island nation of Madagascar in Africa, or always in Madagascar, this nice-looking house, which is, a small house, 3 bedrooms, and a garage and 1 bathroom. And inside this house, you find 125 micro workers that day and night perform tasks for all of us. They perform tasks in the room, they perform tasks in other places, they perform tasks in the garage. Now, usually there are windows, which is good news. But again, the working conditions are not perfect. And this, we'll see, is a long story that bridges that gap that I identified at the beginning. There is probably something halfway between the computational and mechanical part or hardware part of what we do with AI and the data part. And this is what revolves around now big digital infrastructures like Amazon Mechanical Turk. Amazon Mechanical Turk is not big. It's like 500,000 persons working, but you have other platforms in China or in Australia that have 12, 15 million workers, and the long history leads back to, once again, a very Viennese story, the story of the Mechanical Turk. I understand that some of you are familiar with this. Raise your hand if you are. Okay, yes, of course, I'm in here. For those who don't, and were probably, well, I mean, this was the first artificial intelligence, supposedly. There was a chess player disguised as an Ottoman Turk, and this was capable of simulating human cognitive processes and beating chess masters at their game. There was, of course, a hidden ingredient. In this case, a secret ingredient was somebody that was hidden inside the machine. You see that there is a person hiding there. Who was this person? It's a matter of speculation. Some people said that it was a small person, like a person with dwarfism. In other cases, it was a very skinny boy. According to Edgar Allan Poe, who was a phenomenal racist, that was an Italian who was brown and a hunchback. So, I mean, come on. Anyways, in any case, never a person who was considered a master at chess. And this is the point that I want to make, that there is an intrinsic connection between the computation and algorithmic part of AI and ML, but with the computational as a human-based activity. The human-based activity that is necessary to produce what we call machines. But how do we define machines? Well, machines too have a long history. I won't go into that. I just want to provide you with probably the first definition of machine that comes from Vitruvius, first century of the Common Era, before the Common Era, in his treatise De Architectura, which means about architecture, he said that a machine is a device made of solid pieces of wood which exerts the greatest forces towards moving weights. Okay, so a very specific definition. It is about, well, it's made of wood, okay, it was a long time ago, and importantly, it is about moving weights, it is about moving physical entities. We might measure the difference between that machine and our machines. They are made of code and they move around, mathematical entities to an extent, or data entities certainly, and this kind of long way from that machine to this machine was somehow facilitated by certain well-known figures of the history of science, like Galileo Galilei, or some institutions like the Académie Royale des Sciences in Paris. They, between the end of the 16th and the beginning of the 18th century, started putting together machine and computation. It was important to calculate mathematical entities and empirical entities, and to process empirical entities mathematically, to achieve an effective machine. In order, for instance, to calculate how divergent was the performance of the machine from the theoretical performance, and also to see if the machine is worth producing. This is a striking change in the Western perception of what a machine is, because before that, machines were considered basically tricks, illusions. The Greeks called them thaumatas, which means marvels. Marvels because they were a spectacle in order to create a sense of wonder. And this is something that changes so much that with the first industrial revolution, the machines are presented as exact entities that are based on calculation. The problem is that, according to some historians and scholars of science and technology studies, there was a lot of illusion in those first machines. For instance, if we look at the first spinning jenny, or any kind of machine that is used in the production of fabric without the help of any human being. That was the commercial claim of this machine, which was produced, or at least presented, because it was just an article published in a French publication called the Mercure de France in 1745, and this was somehow the first machine that was insisting on the fact that we can get rid of human beings, we can get rid of workers specifically. This was the Vaucanson machine. Vaucanson is probably more, you are more familiar with this inventor, because he was also the guy who invented the robot duck that defecates, which is probably a more entertaining machine. Anyway, according to him, the future of manufacture is a factory where one sees the fabric weave itself on the loom without human intervention. The warp opens, the shuttle propels itself through, the reed pounds the cloth rolls itself into the cylinder. So a lot of automatic processes there. The problem is that, according to Edward Johns Imhotep, who is an historian, this entire description is based on a set of erasure, a set of, let's say, again, processes that hide the work of several human beings, not only those who were necessary to produce the actual loom, the actual machine, but also those who are necessary to operate it. According to Vaucanson himself, at least one person was always needed around that machine. That person was presented as an unskilled worker, but a worker that was performing computation. He was a worker, well, she was a worker, because according to machine, this was such a simple job that even a small girl could do this. And think about of how misogynistic and discriminatory this example is. Even a little girl can do this. That basically consists in counting from 0 to 10 and clicking on specific talks and buttons. Now, seeing the machine as autonomous, as several historians have pointed out, is a convention, but a convention that is based on calculation. In order for this machine to work, we need somebody who does very, very simple computation. And this is the important part. Every time in the history of human computation, we have described the work that is necessary to make this machine, function. This work is usually allocated to persons who are described not as exquisite data scientists, well, before that, anyway, exquisite scientists, but as low-skilled workers. In some cases, workers that were considered like the lowest wages, like clearly women and girls in particular. And in this case, and I want to skip the rest, it is important that we point out that in order for these machines to exist, in order for the machines to be autonomous, we need the hidden labor of some low-skilled person who computes. This is important. This intuition was eventually developed, well, a few decades afterwards, by this other very French guy by the name of Gaspard Riche de Prony, a nobleman that during the French Revolution found himself in a strange position. He was charged with the responsibility of producing the logarithmic and trigonometric tables for the reformed French cadastre, which is one body that deals with land and taxation. And the problem was that the French revolutionary had changed the measurement of angles from 360 to 100, which of course implies a lot of conversion. So how can we do it? How can we produce accurate tables to calculate logarithms and trigonometric functions? Well, he came up with an idea that basically he copied from Adam Smith. Adam Smith, the famous economist, who came up with a description of the pin factory, the factory of small nails and pins. How can we produce pins in an effective way? Either we have one person producing the pin from the beginning to the end, but the performance is probably not that good. We can produce just a limited amount of those. Or we create a system of division of labor. We create a manufacture where we have 18 persons, and these 18 persons do one thing in which they specialize. Basically, he took this idea and transferred it to human calculation. And he created the first computing factory, which is not a factory that produces computers, but it is a factory-based or manufactured-based structure, a big office basically, where you have hundreds of people computing, meaning making calculations. to produce these tables. Basically, the idea was based on these organizational charts. At the top, there was a scientist, of course, and in this case, the scientist was not even Gaspard de Prony, but somebody who is extremely proficient in modeling the calculations that we have to do. Then we have planners, people who take this abstract view of the function and turn it into a set of operation and delegate these sets of operation to a bigger army of computers who are human again. These computers were people who were out of job during the French Revolution. According to one historian, they were basically wig makers. Wig makers, you know, the wigs that in the 18th century were extremely common among the noblemen, unless they lose their head because of a little thing called the guillotine. And so you had several hundred persons in Paris who were unemployed and that were promptly employed as computers in this case. Well, this idea was again taken by somebody with whom you are definitely more familiar than de Prony, a guy called Charles Babbage, who eventually was confronted with a little problem. Okay, this de Prony idea is very, very fancy, yet I'm pretty sure that we can do something to minimize what he called the mental labor. The mental labor is the human computation. So what do? Well, basically we do the same thing that happened in the manufacturers. Instead of having the division of labor between humans, let's divide labor between humans and machine and introduce the machine in the mix. And this machine was, of course, the analytical engine that he tried to develop to, again, get rid of this human computation. The problem is that it was not very successful, not during his life. You're probably familiar with the fact that Babbage in the end failed to produce these, and also failed because he was confronted with several adversaries and enemies of him from the scientific and human point of view, like this guy here called George Biddle Airy, who was the director of the Greenwich Observatory, a prestigious place in the UK, for a striking number of years. And this guy was instrumental in making Charles Babbage endeavor fail, because he was the guy who was charged with reviewing the progress of his analytical engine, and he said, okay, this is just useless. We can go on just using human beings for this computation. They are cheap, and personally, I, George Biddle Airy, have devised a system that optimizes the process of distributing calculation. How do we do? Well, basically, we do the same thing that we've been doing in the production of, I don't know, textile. We take people that work from home and we send them the pieces of calculation that they have to perform, and they send it back through the mail, and we pay them. We pay them by piece. So they were paid as piece workers. They should, in this case, possess some skills in arithmetic, logarithms, and elementary algebra, but don't mistake this for some kind of specialization. On the contrary, those who were working from home, and the very few that were working also from the Greenwich Observatory, were considered as working class grunts. And this is important, and we see an element or an evidence of this when eventually in 1894 there was a terrorist attack, or attempted terrorist attack against the Greenwich Observatory. A French anarchist decided to put a bomb into the observatory, and he failed. The bomb eventually exploded before he could reach the observatory, and he died in the process. And the first persons who came out of the observatory, well, the only persons who were still working after, at night, at, 4:45, at the time was night shift, were two computers. And these two computers were considered as possible suspects. Possibly they were like the, inside men that were helping these terrorists and were interrogated by the London Metropolitan Police, and eventually they said, okay, yes, no, we have a certain set of grievances because our job is crappy. Our job is basically a job with no future. We earn very few pounds and shillings, actually, and especially what we do here is not transferable in other parts of the labor market. So these were somehow captive, low-paid persons, especially several of them were, an increasing number of them over the years actually, were women who were recruited for, some very, let's say, cynical calculations in terms of, these women could be paid less and they would not complain, especially because according to the laws in the UK at the time, after marriage you are supposed to stop working, and so they would eventually work a few years and then go on with their lives. This is something that is very common. It's not only an English social phenomenon. Another example of the recruitment of women to perform this kind of data work before the actual data work started was the development of what sometimes are referred to as sky charts, les cartes du ciel. Sky charts are basically maps of the sky that are based on photographs of the sky. The idea is that you take a photograph, you project the photograph on a grid, and then you have to calculate the distance, and then you have to calculate other things too. This was the somehow the ancestor to labeling processes for images that we have today in any ML operation that involves, for instance, I don't know, self-driving cars or dog filters for Instagram. Sorry, filters that put you a dog face on Instagram, not for your dog. These first data workers, surprisingly, were recruited among women who were definitely underemployed, or, okay, let's say that had a weaker negotiation power in the process. One example was teachers in Bordeaux, in France. And in the Vatican Observatory, surprisingly, even nuns were hired, recruited to do this. I insist on the fact that hiring is probably not the right word, because this was not conceived as an employment. If it was, these persons were definitely paid a lot less than their male counterparts. For instance, in the Harvard Observatory, the persons who were doing this kind of data labeling were paid 20% of the man's salary. And the important part is that this is the moment where we start seeing another important element, the fact of essentializing this women's work and saying that we don't need to pay them a lot, and this is something that will eventually play a role in the hidden figure discovery. We don't need to pay them a lot because somehow these women do it naturally. It's clear and obvious that they are more detail-oriented than their ADHD male counterparts, and they are more dedicated, and they are not easily distracted, and they in some cases there were also insistence on the fact that they have small hands and they can write smaller figures and stuff like this. This also means that the process of the recognition of the actual scientific and economic value of this work was a long and painful one for especially women, because they were relegated in a role of obligatory amateurs, meaning they were forced to stay amateurs and not become actual scientists, despite the fact that some of those had responsibility roles, like for instance Gertrude Branch, whom you see represented here, a mathematician in the US who was responsible for setting up one of the most incredible examples of a computation factory in the 1930s in New York. This was part of, let's say, a poverty release and unemployment release plan launched in the framework of the Roosevelt's New Deal. So the idea is that after the Great Depression, we have several persons who are out of job. What do we do with them? Subsidize them? No, that wouldn't be American. Let's put them to work for a smaller salary in a job that officially does not exist. And this job was actually producing the US mathematical tables. So they were set in a New York-based former factory. Was not the most healthy place in terms of safety and regulations. We were not up to our standards. And basically they were 450 persons who included especially women, but also people from specific minorities, like, for instance, Jews, Irish, and people of color, persons with disabilities. And those persons were paid remarkably less than well, any other person that was performing an average job at the time. We're talking about $20 cents per hour. And the interesting thing is that, do you know how much, according to the most recent estimates, are paid data workers today? For instance, ChatGPT workers in Kenya. They are paid between $1.34 and $2 per hour. I think that given the differences and changes in our economies, we are still on that level. Just to give you another example that comes from my own fieldwork, the persons that I showed you in Madagascar, they were working for something like 96 euros per month, which again here in Vienna you wouldn't even buy a dinner with it, but in the argument that is usually used is, well, okay, they're in Africa, it's not the same. I can tell you that in a big city like Antananarivo, which is the capital of Madagascar, 196 euros is not enough to live by yourself or with a family. And some of these people were telling us, we hope that by the end of the month we will receive the distribution of rice, sugar, and coffee, because otherwise we cannot go on, like general necessity, general food. Okay, when does this change? Well, of course, this changes when the mechanization and the introduction of electronic machines changes entirely the activity that is necessary to produce calculations and to produce accurate calculations at that. But importantly, what happens around the 1940s and 50s, where usually we see in the standard histories of computation that, in the UK, for instance, Alan Turing was instrumental in creating Colossus, which was basically the first computer, which, of course, eventually became the big mainframes of the 1950s and 60s, and then we miniaturize until we arrive, well, we know, to our smartphones. It's not actually like that. I mean, it didn't happen like that exactly. If we look at what happened around Alan Turing's activity, for instance, during the World War II, when he was working in a facility called Bletchley Park in the UK, he was actually coordinating a team of human computers. They were called the GIRs. Again, we're still back to the little girl of Vaucanson in the 18th century. So Alan Turing's activity was the role of the scientist that you saw in Gaspard de Prony's organizational chart. He was basically producing and splitting the most complex calculations in smaller ones that could be performed by others. But the introduction of Colossus, this first machine that was able to decipher, to decrypt the secret codes that the Nazi were able to produce with their own machine Enigma, actually was a clear example of why these GERs were so necessary at Bletchley Park. Because actually Colossus did not simply decrypt the messages. What the machine did was take the complicated Enigma-produced message, decipher it in a simpler message that would be decrypted by hand, let's say, by the persons who were working with Alan Turing specifically. Now, this is a way of ending my presentation. You see Wittgenstein's face, so we're back in Vienna. We started with Vienna, we finish in Vienna, and this gives you the illusion of structure. Now, why is this important? Well, it's important because actually the final controversy, the final, let's say, confrontation, theoretical confrontation between Alan Turing's vision of what computation is and Wittgenstein's view of the same process is, in my opinion, extremely interesting because it represents this story of computation, the Turing's one, the one that we are already familiar with, and the counter-history that have been attempted, although clumsily, to present today, which is embodied by Wittgenstein. Alan Turing in 1936 presented at the London Society of Mathematics a famous paper called Uncomputable Numbers, which basically started with this very bold claim: we may compare a man in the process of computing a real number to a machine. Of course, a lot of things, let's say, derived from that, but importantly, this was not a claim that was flying well, let's say, with people like Wittgenstein, who eventually, a few years later, decided to, reply to his colleague by saying, well, these Turing machines are basically Dimension welche kalkulieren. These are human beings that are in the process of computing. And this is basically the foundational cleavage, the difference, the gap that exists between the history and the counter-history of machine learning and of artificial intelligence. Because basically we are looking at a process that is both computational in the sense of computing power, algorithm, fine modelization, parameters, libraries of software like we are all using today. And on the other side, we have this other, always overlooked and yet increasingly, let's say, on display process that involves humans in the loop, and these humans are usually persons who do it for not a lot of money. And this is also one way of saying that this is our contribution to the general history and counter-history. Basically, what happens today, and this is my very final slide, is that the Depronese organizational chart has changed in the sense not that all these, bottom of the pyramid level of the computers has been replaced by machine computers, but that underlying these machine computers, in order to make these machines work, we have to create another level, another layer, another bottom of the pyramid, where we have all these persons that are working from countries like Venezuela, Madagascar, Bolivia, Colombia, all places where we've been interviewing people. They do it for a few cents. They do exactly what observers and charters and astronomers were doing in Greenwich, Harvard, and in other places. And this is an important activity that cannot be considered as, well, a detail of history or a set of persons of which we can eventually get rid of. We will not get rid of them. This is necessary calculations. Whenever you train something, you need to retrain it. You need to verify what your algorithm does. You need sometimes to give a little push to your algorithm, and all this is done by hand by persons who are paid less than $2 per hour. Thank you very much. The silence. Okay, one person. It's probably better if you wait for the mic, because there are people attending on YouTube, I think.
Hello? Oh,
Yep.
okay. Thanks for the talk. It was very interesting. My question goes in the direction of what is the justification or the cause of this paying people little money for essential work? Mm-hmm. Is it because the people that are paying these task workers have an inherent belief that this is just very similar work to what a computer does? It's very simple, and therefore they're paying them very little?
Computer meaning a machine, an electronic computer.
Yes,
yes, of course, yeah.
Or is it the other way around, that because they're paying them very little, that they sort of view it as a
okay.
very...
Nice, yes. Okay, I think that I made it sufficiently clear that there is a long history of paying these people very little. So, of course, there are some, let's say, inertias that go into this. The fact that they were paid a few bucks 2 centuries ago, why should we pay them more than that? Then there are also other non-historical trajectories, and I would point out the colonial one or post-colonial ones. In many of these cases, these countries are not only lower wage countries, but they are also countries that have some kind of economic dependency from the countries where AI is produced. If we look at the map of the places where AI is produced, apart from some emerging countries like China and India, we mainly have countries of the northern part of the world. And if we look at where data is produced for the machine learning products that are put on the market by companies in these countries, well, surprisingly, you see that, for instance, companies in the US recruit persons in the Philippines and companies in the UK, people in India. And if you look at the French, who are, of course, they have their own colonial problems, and post-colonial ones at that, they somehow recruit persons in former colonies, like Tunisia, like Morocco, like Madagascar, again, or Cameroon. And this is, of course, an important thing to point out. And the final thing that I would, the final element that I would stress is the fact that there is also one industrial history of industry, let's say, justification of that. And basically that the persons who now are performing this type of platform-based data work 10 or 20 years ago, probably not them, but their older brothers or parents, would be employed in call centers. And 20 or 30 years before that, probably their parents or grandparents would be working in some outsourcing facility for textile or in other industrial operations and other sectors. Now, and this is important, again, this outsourcing has a long history of economic exploitation, let's call it like this. And this explains why these persons are paid so poorly as of today. Sorry, and while we wait for somebody else, and because they are paid poorly, they are considered as low-skilled. But I insist that this is, you need a lot of skills to do this.
Other questions?
Very good. My job is done here. Thank you very much.
Well, thanks. I think we have a break now, right? So I think the buffet is open. This is what refreshments and see you at, when do we start again? At 4. We'll continue at 4.
Ja. Ist das ein HDMI-Kabel oder? Sind Sie der nächste? Ja, genau. Dann könnte ich das ja einfach mal ausprobieren. Gleich mit Ihrem probieren? Ich probiere das mal so, ja. Weil ich habe nämlich... Das knackt, ne? Oder?
erfahren. Ich tritt damit heute halt auch auf.
Nein, ich habe nur, ich habe mich nicht mehr erinnert mehr.
All right, we will continue. Take your seats. All right, so now good afternoon also from my side. My name is Stefan Woltran. I'm co-director of the Center for AI and ML. We are organizing this event this afternoon. And it is now my great pleasure to introduce to you the third speaker, which now is so to say associated to the first pillar of the three pillars Clemens mentioned in the beginning, which now goes a little bit towards symbolic AI, or at least how symbolic AI methods can be used for things like causality and trustworthiness. Let me say a few words about our speaker now. Professor Nejdl is the head of the L3S Research Center, which is placed in Hanover and Braunschweig, and which is he's also head of the Leibniz AI Lab. During his career, he had several positions as a associate professor or visiting researcher in many prominent places, to mention just a few: Xerox Park, Stanford University, University of Illinois at Urbana-Champaign, EPFL Lausanne, or Politecnico di Milano. But maybe most importantly, he was educated at a university called TU Wien, where he received his PhD in 1988 and stayed here until 1992, and if I'm not completely wrong, in our group, in the DBI group, right? Yeah. So without further ado, I mean, it's really great to have you here, back in Vienna, and yes, the floor is yours. Thank you, Wolfgang.
Thank you very much. I'm happy to be here. Every time I come back, I see something new. I have never been on this floor, right, and in this building. As a student, that was like Getreidemarkt, where some lecture halls, right? Down. Now I'm in 11th floor, so that means I'm growing up, which is a nice feeling. Okay, good. Let me talk today about causality and the role of causality for trustworthy artificial intelligence. I think many of us think they understand what is causality, and I will also not go into detail into all the definitions. I have a colleague from the group or Institute of Philosophy who actually wrote a book about causality and physics, and asked, do we really need it? Because in physics, they have just equations, right? No causality there in a sense. But still, in a way, we as humans think in terms of causality, and we'll see it also useful, not only to explain, but to build better models. And in that sense, I connect a little bit to the first talk, even though I must confess I never went so deep in mathematics, so I'll stay a bit more on the surface, but causality is useful also in that context. Let me start with a motivating example, right? So this is actually a paper which is called Storks Deliver Babies, p-value is 0.008. That was published in 2000. That was not really a scientific paper. We all know this is not true, even though it has a highly significant p-value, right? On these 3 pages he showed it. You can find a nice correlation, except in this case there is a confounding variable, which is the size of the countries, which kind of increases both the number of population and babies and number of storks, right? So, but if we forget about this variable, we are somehow in trouble, right? And we are also in trouble if we look at the statistics about drowning deaths and ice cream, right? So whenever ice cream consumption goes up, people start drowning, right? Which is really bad. So we should forbid ice cream, which would be really a pity, because it's not really true that ice cream causes deaths by drowning. It's just correlated, right? Because it becomes summer, it becomes hot. Everybody goes to the sea, eats some ice cream, goes in the sea and drowns, right? So this is life. Sometimes really bad, but there's a clear correlation. And also, I was interesting to see how the divorce rate in Maine is actually highly correlated to consumption of margarine. Right? Don't know why, and I don't know what causes this, but I mean that's what you can find out, right? And so this is correlation, right? So and it's and that happens if we just see what we see together. And there has been an area in machine learning which is about adversarial examples, where people try to fool machine learning systems, right? We know right now that they really work very well. Many cases. Sometimes they work better than humans. Sometimes they are also easily fooled. And so there's a nice paper which was published 2019. I think that's the MIT group. Adversarial examples are not bugs, they're features. Why? Right? So he talks about a planet ERM. Maybe you recognize this, empirical risk minimization. Right? We had it in the first talk. And there is this race which is called the nets, and they are really good in finding patterns, right? So Darwinian evolution made them actually perfect in finding patterns, right? And you find patterns everywhere. I mean, we just had 3 examples where we find these patterns, right? And so, for example, they are working on this kind of interesting image data set, which I think that might be CIFAR, right? I'm not quite sure, right? They are blind, so they are just able to kind of see pixels, right? They don't know what it means, right? No, that's not CIFAR. That's I don't know. Does not matter. So they just get these pixels as inputs, and then they get classes of which they don't know anything, right? And then they should optimize putting these images into these classes, right? They don't really see the images, they don't understand them at all, they don't understand the classes, right? They just try to find patterns, right? And so, for example, they come up with this pattern which is called a togit, right? So on the upper level, you see this togit is easily visible, right, or not. So that's what they find, right? And then they have this other pattern, which is the gap pattern, right? And so and if you overlay this, they put it on this other picture, and this pattern stays, right? And they say, okay, now if you put this pattern into the picture, then this is the pattern, right? This is recognized. And the trouble for us is that these patterns don't mean anything, right? But for them, they mean a lot. And so they just go by these patterns and not by what we see, right? And therefore, you can actually get a system where you change a little bit of these pixels to make them believe this is another pattern, and then they say, okay, this is another pattern, and we don't see any change, and we are surprised why the machine learning system works strangely, right? And Madri and his students go on in this paper and say, okay, so really it is the case that we are kind of course, working with what he calls robust features, which are really correlated with the classes, right? So if we want to classify animals, we look for ears, snouts, etc., right? So this is what we understand. And that's one way to classify this picture. It works quite well, right? We are good pattern recognizers as humans, right? But there are these other features, right, which look like these strange patterns, right, which are also there. And we call them non-robust features because they are, in a way, just present in this test set randomly, right, or by chance, right? But they are there, right? So if I put this test set into the machine and run this ERM optimization, right, it might be that these features are a little bit more predictive than what we see as, or that what we recognize as ears and snouts, right? And so that's it, right? So that's everything to know in this context, and that means actually this is a dog, right? You would say this is a dog, okay. But there are also some features in there which it has in common with a cat, right? We don't see this, right? It's this kind of invisible pattern, right? And if we, for example, that's an interesting experiment in this paper, if we, for example, label all the dog pictures with cat and all the cat pictures with dog, right? We also get a good classifier. It's not quite as good as the original one, right? But it forces the machine learning algorithm to go back to use these kind of invisible patterns, right? Okay, that's interesting. Now, these were just the introductory examples, and you might say, okay, what is wrong here? And in the first examples, but also in this one, we are actually relying on features and on correlations which do not mean anything, right? So maybe that's the reason why we could possibly see and look at causality, right? Which is signs of cause of effect rates. So if we come with our ball on the right side, then the ball on the left side goes away, right? So, okay. And this has been mathematically, or also from a computer science point of view, really nicely been discussed in a book which is called Causality, which first came out in 2000. Judea Pearl, some of you may know him. He invented Bayesian networks, right? So which are these nice graphs which tell you how variables influence each other. So the Bayesian networks actually do not say how one variable influences the other in the way of causality, right? It just says, okay, if I have a set of variables, how can I, and probabilities on their values, how can I compute the probability and values of another variable, right? It has nothing to do with causality. And at some point he realized this, right? After having invented Bayesian networks, he said, oh, what have I done, right? I have to go further, and he kind of invented, well, he did not invent causality, but he invented the formalism, the do calculus, which generalizes Bayesian networks, which introduced causality. And there's this ladder which you saw in the first picture, which I show also in the next picture, which has these three levels. Okay, here's the ladder again, right? On the lowest level, there are associations, right? Correlations. And this basically means I look at my data. I look at my data and see, I look for correlations, basically, right? And then if somebody tells me classify something, I try to find correlations of features with the class. And I optimize this, obviously, right? So this is what I'm doing here. And so this is very useful, right? So if I'm a doctor, if I see a symptom, then what does this tell me about the disease, right? Or if I have a survey, what does it tell me about election results, etc., right? If I have a training set, right, what are the classes? What is the function which actually maps examples, features to class, right? This is really very useful, and this is underlying most of machine learning, right? So nothing wrong with that. But there's something else in the real world, right, which is not included in this picture, which is doing something, right? I can do something, and if I do something, it changes the world, right? And it changes what I see, it changes my observations, right? And so these interventions, as I mentioned, the do calculus, right? So this is what Pearl introduced. Given that you do X, right, or you set X to a certain value, what effect does this have on Y? So I don't just look at X, right? Looking at X doesn't change it. Doing it can change it, right? That's an intervention. And so that this is what I can do in this context. And then I can answer the question, what if I take aspirin? Will that help my headache? Should we ban cigarettes, right, to avoid lung cancer? Yeah, let's look at it later in more detail. And then there's the third level, which is counterfactual. That is, what if? What would have happened if something else is different, right? So what would have happened if I would not have gone to Aachen in 1992, right? I don't know, but it's an interesting exercise, right? So this is this third level, and I'm thinking about hypothetical worlds. It's difficult to answer them, right? But you can do some reasoning on this. So this is the ladder once more, which implies the higher we go, the better it is, which is not always the case, right? But I mean, just for this talk, let's assume higher up is better, okay? Now, it's not really that Pearl invented causality, right? And it's not really that people did not rely on it, right? So if you go into medicine, this is actually an important thing, right, to consider, right? You are not interested in finding out what is correlated. You are interested in how to treat people, and treating people means doing an intervention, right? So people at some point did not know about what causes skorbut, right? Now we know it's vitamin C. It's lack of vitamin C, right? So the intervention would be give vitamin C. So they did not know this. Nobody knew what a vitamin C is, a vitamin is, right? So what did they do, right? So they kind of took, I don't know how many, 20, 30 sailors, right, who had skorbut, right? And then randomly assigned them to 5 different groups, and some got salt water to drink, right? And some got other things, and the lucky ones got lemons, right? And the ones with lemons got better, right? And that was clearly an intervention, an experiment in that case, and this is what medical people are doing all the time, right? In a way, if you do a clinical study, this is what you do, right? Actually, this is random control trial, or this is also what a big search engine can do if it wants to find out, is it good to change my user interface, right? Then what do? You randomly give 10% of the users another user interface, right? So really randomly. And then you check, is there a difference in what people do, right? Do they, I mean, click faster, or I don't know, whatever you want to check, right? But you put people into 2 different groups randomly. This is important. And then we see whether this intervention, this change in a way, right? This is just one change, what makes a difference or not, right? So this is a randomized control trial, right? I get a lot of people, do a random distribution of them into 2 groups. One I call control group, the other one treatment group, and they are otherwise, so basically they are the same, right? A lot of people, I mean, they're not really the same, but I try to make these 2 groups as similar as possible. This is why I use dice, right? And then the probability that a certain person is in control or in treatment is the same, right? So in a way, I split them evenly, and the only thing which really the people in one group have in common is this treatment or not, right? And this is what you want to test, and you want to see whether this makes a difference or not. Now, if we could say that's it, right? So let's just do random controlled trials. It worked after all in medicine, and this is what we should do. But sometimes that's not really possible. Sometimes maybe you don't want to do that if you are already kind of, it's very probable that the treatment will actually be helpful. Then maybe it's unethical to give half of the people some placebo, right? I know they will die, and I'm not sure, but I think the other will get better, right? So maybe I should not do that. But if I don't do it, I don't get the my treatment appropriated. Right? I cannot use it afterwards as an official treatment. Sometimes also, I mean, there have been these discussions, right? Is it good? I think in Vienna that's actually a good example, right? So there are some Catholic schools, not very many, right? In Hanover there would not be any because they're all non-Catholic, right? So really terrible. But here you have Catholic schools, and the people the parents who bring their children to the schools, sometimes maybe think these schools are better, right? And okay, now you could just take the pupils which go in the Catholic school and the other schools and see, right, outcome which go on to, I don't know, whatever you want to measure, to university or grades or whatever. But here you have actually now a selection bias, right? Because certain children will go to these Catholic schools. Maybe they have a really good background, and it does not really matter whether they go to school A or school B or school C, right? They have just a really nice family, and they would learn wherever you put them, right? So it's actually wrong just to take these two groups, children from Catholic and non-Catholic. But you cannot change it, right? You cannot, for an experiment's sake, say, okay, now you go to this other school for 1 year. It will certainly be bad, because if you move child from one school to the other, it will go down, right? So cannot do it, right? So sometimes you just have only this data which you cannot change. And then the question is, what can we do? Okay. And if you are Pearl, or if you believe in Pearl, right, you say, okay, I need a causal model. There's also something which is called potential outcome framework, which tries to simulate this randomization, like in this random control trials. I will not do that today. But yeah, okay, let's use a graphical or a causal model, right? So if I use a causal model, it looks like this. You remember this Bayesian networks, right? So for the moment, we just see it as a Bayesian network, but we really also want to treat these edges as causal edges. And so H influences two variables, and T and Y. I don't know what these are, and T influences Y. And so then if you just, okay, so that's something you can write down. Or maybe age and gender has an influence on these two variables, or maybe age and stress, right? And then if you want to check how stress influences Y, you actually should look at the other variables as well. So let's not go into detail here, but this is a Bayesian network or a causal network if these edges are causal, which means one variable causes another variable. And so there, actually, being a computer scientist, we always look for structures. So you find structures in these networks, right? And one structure is a chain. X influences Y, and Y influences Z, which we call a chain. Okay, why not? We also see something which we call a fork. X influences Y and Z, right? This is kind of this hidden confounder. If you assume X is Y is people drowning, Z is ice cream consumption, right? Then X would be time of the year, right? And if you forget it, then obviously you are lacking something. And then this is, I would call it a collider. There's this kind of funny name which calls it immorality, right? You have two parents and they go together and they're not connected with each other, but let's call it collider. That's the more correct way. right? A collider means this is influenced by two parents, two variables, right? Which are independent, right? X and Y, Y and Z do not have anything in common. They just influence X. But if you know X, they are somehow connected, right? Through X. And it makes a difference then also if you want to reason about X and about these three variables, right? So, because we and Pearl want to know which variables are independent, and I know that if I have this chain X, Y, Z, clearly they're not independent, right? X influences Y, influences Z, but I can block this path, right? How do I block it? I can say, okay, I know the value of Y, right? And then X does not matter anymore, right? Because it blocks the influence of X on Z, right? So if I have the value of Y, this path is blocked and X and Z are independent. For this association, it works the same, right? So Y influences X and Z, and so X and Z are related, right? Are dependent, right? If you know something about X, right? If X goes up, right? Also Z will change, right? Because they are connected. But if you fix Y, this does not work anymore, right? You block the dependency. The funny thing is with collide, it works the other way, right? So if you don't know anything, right? If you don't know Z, then X and Z are independent, right? They are not connected anyway, right? They are indirectly connected to Z, but you also don't know anything about Z, right? So X and Z are independent, but if you know Z, they are connected through this, right? So you, and if you talk with statisticians about conditioning variables and about these effects, then usually their suggestion is, okay, condition on all the variables, right? Because you want to block all these paths, right? If you block on all these paths and you have this collider in there, right? It's bad, right? So don't unconditionally block everything, right? So this is, and here this is, for example, if you want to understand how T influences Y, you cannot be sure because you have all these other passes, right? You have this influence through C and you have this influence through B, A, W. But you can block this, right? And if you block this, which means you just observe these variables, then you can look at your data and you find, yeah, you can investigate this relationship, how T influences Y. And if you have data, right, that just means, right, you set these two variables A and C to a certain value, right, or it's already set in a certain way, and you look at this subset where A has a value, and then you look at and C has a value, and then you look at the relationship you want to investigate, right? So that's actually useful. And Pearl calls this backdoor adjustments. And I'm almost finished with this first part. There's something which is equivalent, so you can work on these causal graphs, and you have to add what Pearl calls the do calculus, which I did not really show. But there's this other formalism which is called structural causal models, which just basically say you have these functions, and it's not a mathematical function, it just means there's some function, right, which takes A and gives you B, and to make this stochastic, you introduce these noise variables. Who is the noise variable? And then it looks like this, right? You basically have a formalism which is very similar to what I just described. So forget about this now. Believe me, there's a formalism. Read the book of Pearl, 2009, right? It's 300 or 400 pages, so it's a lot. I did not read all of it yet. I still have some time, right? I actually want to talk about causality in the context of trustworthy artificial intelligence, right? We all talk about AI, and we want to have AI systems which are trustworthy, right? So how can we do that? And then the first question obviously is, what is trustworthiness? And we did not invent an ontology for this. There's an interesting European big project which is called Taylor. They have a white paper where they describe trustworthy AI and the dimension. We just take this dimension, right? So one important dimension is interpretability, right? If your system tells you something or suggests something, then it would actually be useful if you get an explanation, if you understand what is going on, right? So I will look into this in more detail. Fairness, same thing, right? We always, we have, I think, all read articles about biased suggestions by AI systems. So you should not do this. You are not allowed to do this in certain cases, actually, because there are anti-discrimination laws, and in others, it's just not ethical to do this. So don't discriminate, right? So how can causality help here? Robustness, we saw a little bit in this first paper, which I mentioned about the planet of the nets, where you can construct examples which are a little bit different to the human eye. They are not different, but the AI system gives you a totally different answer, right? And I will look a little bit into that. I will not talk about privacy and safety because my time will be up by then. But if you want to read the whole report, just look it up. It's called A Review of the Role of Causality in Developing Trustworthy AI Systems. It's a review, right? So it gives you a lot of papers. It does not explain the papers in detail. I will give some examples now of these papers, but it gives you, I think, a really good overview of all the ways causality or causality inspires approaches can help you. So let's start with interpretability and add in causality. And why should we actually look for causal explanations? Well, first, I mean, explanations or interpretability is useful. Many people nowadays maybe say, okay, it's not so important because I have this neural network, right, where I plug in whatever I want, I get out whatever you want, right, so that's perfect. Let's forget about what it does. It does not, usually it works, right? Most of the time it will work. But of course, in some applications, it is important to understand why it works and maybe also realize then why it does not work, right? Because as a computer scientist, then you want to debug it if you don't know what it does and why it comes to a false conclusion. You're helpless, right? Also as a computer scientist. And then there's this, I think that's actually written in the, even in the data protection regulation, not in the new AI Act, right? So decisions by machines have to be interpretable, something like that. And I think the introductory examples told you causal explanations are good, right? It's not the number of storks which has increased, which causes the increased number of babies, right? But something else, which I did not tell you. So how can we use that? So in this whole review, we use this kind of classification device or this kind of hierarchical structure which says, okay, in which phase of the machine learning algorithm do you want to do something? So I'm actually, if you have not realized it yet, I'm actually also talking about machine learning, right? So yes, you can actually change something in the beginning. You can work on the algorithm, you can work on the data, you can do something while the algorithm does something on the data, right? So in processing, or you can do something at the end and say, okay, I should massage it a bit, and so then it becomes better. I get my interpretation, or I do something and I give you the explanation. Okay, so there are these different possibilities. Let's just look at some examples. So in the beginning. So if I start in the beginning there's data. We saw this in the second talk, right, really nicely. If you don't have data, you don't have an ML system. And I also mentioned that some attributes are relevant and some are irrelevant, right? So this is a small example. This is a causal graph, if you want. And there you have lung cancer, and on the left you have yellow fingers, and there's a clear correlation in your data, right, that people with lung cancer, right, over the last 50 years had yellow fingers, right? So this is the correlation you find. Why not use it, right? So people with yellow fingers should go to the hospital, have them cleaned, and then they will not get cancer anymore, right? But even if you don't think about intervention, you will actually find out that this might not work so much, so well in the future, because nowadays, if you smoke, you try to hide it, right? Nobody really should smoke, right? So I go outside, smoke a bit, clean my fingers, right? So I will not get yellow fingers. I will still get lung cancer, right? But that means nowadays the situation has changed, and this attribute, this feature of yellow finger is not longer indicative because it's not longer there, right? So I cannot really predict lung cancer as I could before, right? 50 years ago I could do it perfectly, but now lots of people get lung cancer who don't have yellow fingers. And if I look at this causal graph, it's obvious that, I mean, yellow fingers are caused by smoking, right? I have this arrow from smoking to yellow fingers and this arrow from smoking to lung cancer. And therefore I should not use, it's just a correlation, and the confounding variable is smoking, right? So smoking is actually the cause of lung cancer. Funnily enough, I think it was in the 60s or 70s, right? The tobacco firms said it's not true, right? So lots of studies said, okay, people who smoke get a lot of lung cancer, right? And yeah, okay, these studies were true, but the tobacco firm says, no, sure, yeah, they are true, but there's this confounding variable, right? Okay, just come up with a confounding variable, and then you break this causal dependency, right? Well, okay, we have red pearl, right? What should we do with a confounding variable? We just observe it, right, and see whether it breaks the dependency or not. But the clever people, these tobacco people, right, they invented a confounding variable, genetic predisposition, which could not be checked at this time, right? So 50 years ago, there's this gene, right, which both causes craving for smoking, right, but also increases the probability of lung cancer, right? So smoking is not, it does not cause lung cancer, right? And nobody could observe the genome because we did not know how to do it, right? I mean, now we can, but it's a good way if you want to hide causal dependencies, right? Just suggest a confounder which nobody can observe. Okay, so, and so they actually describe in a nice way how these things work. So they do not really invent a lot. All what they say follows from Pearl, more or less. They talk about this Markov boundary. So if you know these blue nodes, right, and lung cancer, everything else is independent, right? So forget about the rest. That's the message. And they put together several algorithms which test this independence and put it in an open source package. So it's actually quite nice. And in this sense, they give you a good way to look for relevant or irrelevant features. It does not work for the first example I gave you with these pixels, right? Because here you have explicit variables. If you have pixels, that's too low level. And if a neural network learns some features, you cannot really describe them. So that does not work in all cases, right? Oh, but still, it's a nice paper which shows how feature selection should take causality into account, right? Just use the right features. This is also what Madri said, and that's actually a good thing. And sometimes you don't also need big causal graphs. So for example, if you think about, okay, you have a recommender system and people, so Netflix, right? So people watch some movies, and they have this famous recommender system which gives you new suggestions, right? And so how do these suggestions work? So on the one hand, the suggestions work by looking for people who are similar to you, right? And then you get something which should interest you as well. Okay, so that's what you would suspect from a recommender system. But there's another reason why you would watch a movie, because everybody else watches it, right? It's the movie which everybody sees, right? So we call this conformity, right? Everybody sees it. I want to see it as well. I'm not so interested in science fiction movies, but everybody has seen Avatar 1 and 2, and so I have to go and see it as well, right? And so the recommendation actually kind of have these two influences, right? What is actually my interest, and how much do I look at movies which others see? And the usual way to do is you learn this kind of interest-based recommendation, and for conformity, maybe you have this bias which you want to make explicit, right? Popularity bias, right? And this means sometimes you want to suggest things which are not so popular to counter that bias. But really, it's not just one bias, because some people are more interested in following other people than others, right? So actually, you should learn also this conformity as something which is individual and not the same for everybody. And this is what they do without going into the details, right? So they have these two sets of features which represent interest and conformity, and which are learned through two pieces of neural networks separately. So you disentangle, right? You put apart the parts which are responsible for suggestion based on interest, and for suggestion based on following other people, and that makes sense. And the only thing from causality you need is make this small little graph and realize, okay, I should actually train these two pieces separately, or these two sets of features separately. Okay. We talked about, I did not talk, we heard about self-driving cars today, right? So self-driving cars are great, except that they don't really work, right? It's more complicated than we saw 10 years ago, right? So this is life. We started with this, not we, but right, researchers started with this idea of having convolutional networks. They're really good in finding patterns. You train them, and then you can really, so you train them, for example, in this example, they started from these videos, and then the output they want to get is in which direction and how much should the steering wheel turn, right? So they have this end-to-end training from pictures, right, images, pixels, right, to steering wheel change. Okay, so this is what is trained. Now, obviously, we know that self-driving is complicated, so we should try to explain it. Yes, there are possibilities to do that. There are these methods which show you what the neural network is looking at. So these are these attention clusters, right? And it's actually useful. And then it can explain, okay, I go to the right because, right, there's something on the left which I want to avoid. So far, so good, only that we thought it's only ChatGPT which is hallucinating, right? But also here, you realize when you look at what the neural network looks, it's not really true in half of the cases, right? So not even in the sense that it's really the case, but so you use this explanation mechanism, which is different from the learned mechanism to change the steering wheel, right? And so this explanation mechanism is something else, right, which you put on top, and then you see that the neural network does not even use this part of the picture, right? So the explanation mechanism tells you, okay, this is what the network is looking at, but in reality, the prediction of the network does not work on that. Does not really use this picture. So what it does is basically, okay, I have this attention, so on the left, in the middle I have this particle of cluster on the left, right? There's this left cluster, and then if you go down, there's this right cluster. And I want to understand, is this really something, a cluster which influences the steering wheel change, right? How do I do this? Right, so they describe in this paper, I can mask this part. So you see then on the next slide, you see the car, which is there, is just blanked out. It's black, right? There's no car anymore. And on the bottom, on the right side, you have blanked out the car which was there. Right? It's also black. Now you could kind of, so, and that's what they do. They blank this out and then see whether the prediction of the network changes, right? Whether steering wheel changes or not. And if it does not change, then clearly this cluster is not relevant, right? If I blank it out. Now you could say, okay, maybe if I make it black, if it's not a car anymore, maybe it still influences something. But let's forget about that for the moment. It's a bit tricky to really do it right in all details. But that's already a good approach, and it's causal in the sense that it's not really causal in the sense that I can then say with conviction that this car is the cause why I should turn the wheel, but it tells me that my neural network uses this part of the image, right, to influence what it does, right, the output. And for that it works actually quite well. Going back to recommendation, this is a bit even easier to explain. So I have this recommendation which gives me phone recommendation, right? And I say I want, okay, it gives me two recommendations. It gives me this phone with a screen size 4.5, battery 3.0, and price 3.0, right? It's just some ordinal scale. And on the left, I see what is important to the user, right? So the user says screen is important, yeah? I give it a multiplicator of 4. Battery is even more important. I give it a multiplicator of 5, and price is 3, right? So this is the weight, right? So if you want to understand what is recommended, what you do is basically take this user numbers 4, 5, and 3 and multiply them with the numbers of the device, and then you recommend the top highest phones, right? Okay, that's easy, that works. Now if you want an explanation, you could say, okay, I should take the explanation which carries the most weight, right? So screen, what weight does it have? 4 multiplied with 4.5, which is 18, right? Battery is 5 multiplied by 3 is 15, and price is 9, okay? So what is most important in this measure? Everybody agrees, right? It's screen, right? 6 is 18, right? That's an explanation. But it's not a good explanation, right? Because if you look at the phones which are not recommended, they're all bigger, right? So if the screen is really so important, why did it not recommend these other 3 phones, right? So something is wrong with my explanation method. So I invent another one which is causal, and of course it's better, right? Because this is the message of this talk. The interesting thing here is that I use this counterfactual thing, this third level. What would happen if I change something, right? In the reality, it does not change. I cannot change it. But if it had a different thing, if for example, the battery would be here not 1.5 but 2.1, right? What would happen? And so here I would, so here my counterfactual is actually, okay, what, sorry. here actually I ask, what do I have to change to make this phone, this first phone, not recommended anymore? And the answer is just change the battery of this other phone from 1.5 to 2.1, which is a really small change, and whoops, you see that this phone is then recommended instead of the first phone, right? And because I changed battery, then the best explanation here is actually battery is what really influenced the recommendation. Okay, that's based on this counterfactual explanation, right? Okay. I should say something about language models because they are really really interesting right now. This is a kind of simpler language model. This is BERT, right? So 2 years ago, you were actually happy if you understood BERT. I do that, but I don't really understand the really big models now, so let's stay with BERT. And if you have a language model, also nowadays, you are actually interested, what does this language model know, right? Okay, you can ask it, okay? You can get a lot of answers. You can, sometimes you are a bit more methodology. So if you're computer science, you want to see, okay, what does it really know? You probe the network at different levels and you try to see what you find, what facts you can find on which level. So basically, this is what you do probing on different levels and see whether you can get the fact out which you want or not. And then you say, okay, this is what the network knows. And you can also actually understand in a way what are the features which the network has learned. Remember, this is important to interpret the features. The network just learns some features, right? You don't know what they are, but if you can interpret them, you say, okay, on this level it learns part of speech tagging. On this level it learns named entity recognition, and on this level something else. And so these are the features which influence the outcome, right? So you look at the different levels, look for these features, and then say, okay, I have explained the neural network. It turns out that's a good way, but it falls short sometimes because there are some features which are there in the neural network, but they're never used. So how do you find out? Again, by intervention, right? So, which is this causal notion, right, on this level 2 ladder. So how do you do it in this case? You basically try to mask out some features, and then you get a changed network in this piece, which masks out a certain set of features, in the sense that all linear derivations from these features are blocked. So it does not block everything, but the linear derivations. And then you basically can find out, right, if I block these features, does the output of the network change or not? This is what we also had with the car, right? So, and it turns out sometimes you get different answers from this intervention-based technique than by probing, right? By probing, you see what you have here is, for example, some other thing. There's a phrase, beginning of phrase, end of phrase, right? You find it in the network, it learns this, but if you block these features, it does not change anything in some downstream task, right? And in this way, you also find out that, for example, near entity recognition is less important but useful, relevant for your task, and part of speech is actually more important, right? And that's how you find out using this intervention-based technique. Okay, let's go to fairness. And fairness means you treat everybody the same in a very abstract way, right? You then, of course, have to define what you mean by fairness and what you, how you detect discrimination. I will not go into this slide, which says this is actually relevant for lots of areas. Let's just jump to one example, which is student admission at a good university, right? So this is a real example at the University of Berkeley. They had student admission, And you know that there are actually quite good anti-discrimination policies at these universities. And so it realized that, right, the students, male students who applied, 44% were accepted, right, for certain population, and only 35 of the female students, right? So this raises, of course, a red flag, right? So are we actually biased against women here in student admission, right? So we have to think about that. And it turns out that actually there is this hidden variable, right, which is this A, and A in this case is A is male or female, and it influences, of course, the admission, but it influences also. And this is what I feared, right? If it influences admission, that's bad. But it also influences department choice, right? Because it turned out, and in this case, male students applied much more to engineering departments which are actually looking for students. They don't have enough, right? And really bright women applied to, I don't know, let's make up a stereotype, psychology, right? Where you have lots of applicants, and so lots of them are turned down, right? And so if you look at the departments separately, right, you realize that in no department there is actually a bias for or against women, right? Just when you put them together, you see it, but it's not true, right? This is called Wise-Simpson paradox, right? We have this confounder which makes this whole set incomparable, right? So you would have to split it. You have to split it on departments in this case, and then you can check it separately, and this is what you have to do. And so they did not have to change anything, right? Okay, one more on this. This is also an interesting paper. Schölkopf in Germany is kind of, let's say, the one who moves forward causal reasoning most of everybody else. So you see him in this author list, and they have written an interesting paper about how to avoid discrimination through causal reasoning. And basically the idea, I don't go into the details, is that some causal paths are okay, so S to R to Y, and this would be kind of then department choice, right? So department choice does influence admission, and gender influences department choice, but that's okay. That's not a discrimination, even though in the end it will influence admission, right? And then you have these other influences which you have to block. So S to Y, so female should not, so if the female student should not influence admission, okay, that's easy because you just block the gender and nobody sees it. But then if you maybe have this other variable which is also influenced by X, I don't know, maybe this could be girls in school take less of these computer classes, right? And then maybe you have a test which kind of takes computer classes into account as a positive feature, right? And that you don't like, so you would like to block it, and the way to block it is you put X to a specific value, so maybe for girls you increase it artificially, right? Okay, I should finish, okay. I have almost tackled everything, so robustness, privacy, I already mentioned this paper. I will come back to this example, actually. I will not talk about statistical machine learning because we had a lot about it. So no need to do it. Let's just look at this one example. Because we heard about empirical risk minimization, right? So this is an interesting paper which says invariant risk minimization. And what they try to do here is kind of put more effort on features which remain the same across the different sets, because we had in the first talk, you have just one training set. But in reality, it's not always true, right? Sometimes you have several training sets, because if you are in medicine, you have different patient sets from different hospitals. And sometimes it's easier to find out from which hospital the patient is, not what the patient has, right? So that's the funny thing. And here, of course, if you have a training set from Europe, then all these cows are on green surfaces. And from Africa, there are a few cows, but there are many more dromedaries, and you have these brown surfaces. So then, of course, if you are this net person, right, it says, okay, brown is dromedar and green is cow, which is, however, not really true. The only thing which does not change, and this invariant, is how the cow looks like, and then you try to find out this set of features, right? I will not talk about privacy. I will not talk about safety and accountability. And I just end in a way with this picture, right? So we should, as computer scientists, not say, okay, I'll do something and then there is this miracle and the miracle gives you this answer and that's it. Let's believe it. We are all believers. So let's not do that, but try to explain what we get. Thank you very much.
So thank you very much, Wolfgang, for this insightful talk. I think we have time for one or two quick questions and then have to move on to our panel. Okay, Antonio.
Sorry, my question is actually an opportunity for you to tackle some of the slides that you skipped. The question can be phrased like this. Okay, many of the topics that you have dealt with are developed in the ethics of AI, fairness, privacy, transparency. Some of those, of course, were those on where you developed and those you skipped. What are the ways of establishing priorities? So how do you decide what to skip and what to keep?
Good question. If you ask me as a researcher, I do what I find most interesting. If you ask me as a responsible person, then I would have to say, okay, let's just think what is the most important thing. I don't really have an answer. This is why I fall back to this first question, but then obviously you have to understand. So I think robustness is actually really bad because these systems are really good now, right? And then if they fail maybe a little bit, right? Sometimes you don't realize it, you believe everything, right? And then 1 in a million it fails, and then the patient dies or whatever, right? And then the system cannot even explain why it came to this wrong conclusion, right? So thinking about that, robustness, interpretability are certainly, for me as a machine learner, two very important aspects.
Okay, so I would say we thank you very much again, Wolfgang. And I hand over now to Julia Neidhardt for our final item on the agenda, a panel discussion. And all of the speakers will be on the panel, so if some of your question has not been answered yet, there's still a chance to ask.
Yes, please. I will just briefly also welcome the audience, just wherever you want. Okay, so we will then have. Kein Problem. Ich glaube, es ist dann schon lang. So, yeah, so this is the final part of today's CAIML Symposium, and yeah, we will have a discussion about also maybe secret ingredients of AI, and also a bit AI and digital humanism. We want to talk a bit about the intersection of AI, society, education, ethics. So my name is Julia Neidhardt, and I'm also part of the CAIML board, and I'm also head of the Christian Doppler Lab for Recommender Systems, and also active in the Digital Humanism Initiative here at TU Wien. And as you see, so we are very delighted to have the three distinguished speakers from now this afternoon on the panel. But so I do not need to introduce them, but then they got complemented by two more very renowned professors. So we have Professor Helga Nowotny, who just said that she has to leave at 6. So I think it's a good also goal for the discussion that we then try to wrap up and finalize by 6. I mean, I guess everybody is then happy about it because it was already a very long and insightful afternoon. But anyway, so still, we can stay then here. There's maybe still some drinks afterwards, I do not know. And we also have our dean, Professor Gerti Kappel, here now on the panel. And although we have a limited time a bit, and they do not need an introduction, but let me still say a few words. Because, so Professor Nowotny, so, I mean, she's very well known. She's the former president of the European Research Council and also founding member. She's Professor Emerita of the ETH Zurich from Society and Technology Studies. And now she's basically in the advisory board of many very important institutions and also, is author. She has recently published a new book on In AI We Trust, I think, And also, so she's very active here and kind of so significant member also here in this whole digital humanism movement in Vienna, and also a very driving force of the visions and the content of this initiative. And also our dean, you know, of course, but just let me say, so she was, has now been dean for several years and also vice dean before, and she's professor of business informatics and head of the business informatics research unit. And also important, so Gerti Kappel started early on also with other initiatives, and she was one of the first, like for really kind of institutional initiatives to promote women in computer science. I mean, this was a pioneer in Austria with regard to these topics. And also she's a big enabler, because without our dean, we would not have the CAIML, we would not have the Digital Humanism Initiative here at TU Wien, and also for a lot of other initiatives and topics. So thanks a lot to the two of you. And as we talk about the hidden figures today, I mean, this I also would like to say, we had the Girls' Day, I think 1.5 weeks ago, where school pupils come to TU Wien and other universities, but in our case, they were at Informatics. And it's so important still that they also have role models and female role models. So and I think here we have 2 female role models. We have more in the audience, but for me, I would like to just underline this. Okay, so this was the introduction round, and then I propose that we have, so as we are a big panel, so and if everybody, there will not be so much time, so but still I have prepared a few topics that are kind of overlapping. And we already had the input of now the whole afternoon, where some of the things were raised already. But I will just start with a few questions. I said in every round I will address one of you first, and the others then can comment. But feel free, I mean, also to adapt the topic how you like, and maybe then even in the end, I do not know, we can also have some questions from the audience. Yes. So what I thought, like, we were hearing in the first talk today also about the advances of AI. We started with this topic, and then the believers, you said this term, which I find interesting, and also that it seems to be a miracle. So we had the miracle in the last talk again, but still, so a lot of things are happening, and you said also that it's very important to understand now what is going on, so that we do not have to be the believers, if I understood correctly. But here I would like to address our dean first. So, like for us as a faculty, as at the university, what new challenges do this pose to us, and how can we also, I mean, there are still some students here, and for us, like teaching, how can we tackle these issues now? Because now things are happening at an extreme pace, and how to also keep up in research, teaching, that we can aim for this understanding.
Education, education, education. Yeah? And we have to start early on, but you were asking me about research and teaching. And let me start with research. And you know, when the TU Wien is famous for this so-called symbolic-based AI part, yeah? Building on logical foundations, on rule-based systems, knowledge representation. The first group has been established here in the mid-80s and went through all the winters of AI, and now we have we are in the summer of it. But there is a lot of research going on on the symbolic part, but we also kind of catched up over the last years on the non-symbolic part. And as we had also this very good, interesting presentation, the first presentation today, there's in fact a lot about statistical foundations, which is also kind of researched here at TU Wien, working more and more things together with the computer science department. So, you know, normally you have these different faculties, and the faculties are acting almost like silos. But over the last few years, at least, people realized that, especially on the foundation level, when it comes to mathematics, to statistics, Bayesian networks, all what we have heard today, together with symbolic AI, the people have to work together. And this is, I think, one of the also one of the goals, and also one of the good things of the Center for AI and ML, which we have established 2 years ago, that we have tried and that we are further trying and hopefully succeeding to tear down the walls between the faculties. You might know that there is also an Austrian-wide initiative to bring together the machine learning and the symbolic AI researchers. There are endeavors to build up Austrian-wide centers for excellence, and they are still to kind of further to be developed. I started with education, education, education. I really think that one of the most important things is that we teach our students the technology, the foundation, but also the kind of the implications of what they are doing. I think all three talks today, especially the first and the last one, has shown us that we have to define what our algorithms are doing. I really like the inductive bias, what you have brought up at the beginning. I guess I have to ask more questions about it. But it is really that you have it in your hand, and we have to teach it to our students. So we have it in our hand, that we have to teach it to our students what they develop, how they define the algorithms, what are the features, what are the functional and what are the non-functional features. I mean, when I started, the non-functional feature was performance. I think meanwhile there are much more non-functional features which we have to teach. So it's really it's really critical that we teach this to our students. We have changed our curriculum. It will start with beginning of this fall, that we have one bachelor in computer science, where it's also possible to deepen your knowledge already at the bachelor level in the area of machine learning, symbolic AI, logic, and theoretical computer science. So we have on the one hand, we have developed one bachelor system in computer science, where it is possible to really, depending on new new areas, to have a very flexible way of deepening in the different, in different subjects. And there AI and machine learning is one of the, as a symbolic AI and machine learning is really one of the topics we are kind of further teaching. But when I said education, you mentioned Girls' Day, yeah? We have to start as early as possible. And there is, since several years now, an initiative at our faculty that we have built up workshops for pupils. We started with the higher secondary school. We are now in the lower secondary school and even go into the primary schools. And there we teach computational thinking. But of course, what is more, or at least as important, is what does it mean having an AI system? What means artificial intelligence? And starting with, again, this fall, we will have new workshops in the area of artificial intelligence at the level of the secondary schools. And you can imagine this is, in fact, what all pupils and all teachers are really asking us for. And I think this is really our responsibility as a university, not only teach the students, but also build up this relationship with schools, what we have or where we are in the middle of the way. Last but not least, you were mentioning digital humanism. You know that we several years ago, it was in fact in our faculty that this initiative, at least at the Viennese level, started. And it will be on Monday that we have this, I was mentioning it, this UNESCO chair on digital humanism. It's the first, just to explain, UNESCO is giving chairs in different areas to renowned scientists, to universities. It's a lot of reputation, it's no money. But never mind, the reputation is very important, the branding, the marketing. And it is really the first UNESCO chair at a technical university in Austria. And we are very proud and happy to also go out with this responsibility we have in general in developing our technical systems, but especially in this area of autonomous and artificial-based systems, and building it with a a responsible mind or a responsible side of it. One way of seeing this digital humanism is also to teach it to our students. And ethics, as embedded ethics in computer science, is also a topic which we are currently further discussing to change our curricula in such a way that we also teach immediately in the different subjects, programming, software engineering, databases, ethical issues. Just one example is, for example, what TU München is doing. TU Munich, they have an own software development process where they put ethical deliberations into the software development process. So it is possible really to teach ethical aspects in different technical subjects. Thank you.
Does anybody of you want to add something to maybe inductive bias?
Just on inductive bias, yeah, I mean, I think it's a dangerous sort of phrase that we used to use and maybe we shouldn't use anymore. But no, I mean, the point about inductive bias is that one needs to have premises in order to learn. One can't learn with a completely tabula rasa. And of course, we need to make sure those biases are not aligned with biases that we wouldn't like to have, but still biases need to be in the sense of we need to have a pre-set of ideas about what might be possible outcomes of a particular investigation or situation, and as flexible as possible, but we need to have some limits on our flexibility.
I mean, as a follow-up to this, I mean, these new technologies and this scaling up, and also you mentioned the scaling up. So how should I say, is it going on like this, or do we need then also, I mean, some different path maybe that you mentioned that you do, as you showed in your first talk, how you try to understand AI, but could you also think of other ways that you think would be required to better understand this new technology now?
I mean, we've only scraped the surface of understanding what's going on. I mean, it's clear to me that there are things being learnt by deep learning systems that are, about the structure of the problem, the structure of the data, that is well beyond just performing well on that particular data set, because that's how it transfers to other data sets. But understanding exactly how that happens and why that happens and what is actually being learned, I think is still, very much an open question.
Yeah. Good. So then I would like to ask Professor Nowotny, maybe regarding the digital humanism, maybe you can, because there is also a lot of students here, and although we have on Monday also this event, but maybe still you can characterize it, what it means in your, so from your perspective, and also how, like one could put it into practice, maybe in an interdisciplinary way also. I mean.
Allow me to come back to the topic of this afternoon session, namely the hidden ingredients. And we heard about hidden figures and hidden people. And this is very important because there is no technology without people, and technology should be for people. But I kept thinking there's another hidden ingredient, and this is what I would like to briefly mention and then come back to digital humanism. We just heard the importance of ethics. We heard your technical efforts, to get something that are ethical related topics like trustworthiness, fairness, etc., into the machine. And it's very important to get a grasp of the technical matters. But I kept thinking, why do we want to have ethical dimensions? Why do we want to have trustworthiness, fairness? Now, if I would ask you, you would say, we are moral beings, we believe in Kant's imperative. There are many philosophical answers. But I think the real reason, and that's the hidden ingredient, is about control. And control is inherent to any technology, because you want a technology to work. That's the sole and most important criterion. You want it to work in the sense that you give it a certain function, you put a goal, and you want to make sure that there is a functional efficiency. The machine should do what you tell the machine to do. Very simple, very basic, very inherent. Now comes the problem with it. Because, first of all, machines don't always work. They break down, there are errors, accidents happen, and they will continue to happen. Errors will continue to be there. So we have to expand the notion of control. And this happened already, and Antonio was showing us pictures of the 19th century, even earlier. There were lots of accidents because the people working with the machines, were not in control of the machine, and the machine was built in a way that did not take into account that people would not control it. So eventually, machines got better. They knew, the designers, but also the ones who were putting them to work knew, we have to think of the people who are working with the machines. So you get all kinds of safety features. And the 19th century is full of it, and there are vast improvements of the safety features of machines. But then this expansion of control continues, because now you are thinking about health. We heard about smoking and other things. We heard about air pollution. We know today all the environmental damages are somehow related to the level of industrialization and the way how we use the machines that have become part of our technical civilization, that has many benefits, but this is where we are now. So coming to AI, it's a further expansion of control that we want. And this, in my view, is the hidden ingredient. why we need and want an ethical dimension, why we want trustworthiness, fairness, etc. Because the difference to the machines, you know, of the 19th century or the machines of the 20th century is that AI has a much stronger impact on our emotional life and our relational life. And therefore, we have to think to expand the control of AI to take care also of our social relations. You know, what does it do to the way how we relate to each other, but also our emotional well-being. What does it do to us? And ChatGPT is only one last example of it. If you have people who are really taken in and think, you know, you are speaking actually to a living being, to another human being, it's just another, you know, a way how the impact of the machine is also visible in our emotional life. Now, control is, wherever there is control, there's also the shadow side of control, namely the illusion of control. And we all know what this means. The 20th century was full of, and modernity as a movement, you know, showed how people have overestimated the kind of hubris that existed everywhere. And of course, it was particularly harmful when it came to the state, you know, with vast projects, and there are very good historical works on that. You know, the hubris, we are in control, and yet it turned out, you know, the large projects did not accomplish what they were supposed to be. You had replacement of people and so on, building huge dams that we now realize are not solving the problems of energy that they were supposed to solve, etc., etc. So this illusion of control is, of course, something that scientists knew from the beginning of modern science, because they had this fear. We cannot trust our senses. We have to make sure that what we observe in an experiment is actually cause and effect. It's actually what we are looking for. So if you go back in the history of science, it's a continuous fear, continuous attempts, you know, we have to control it. And after all, you know, the peer review system, with all its faults, it's organized skepticism. And science has to practice organized skepticism in order to guard against the illusion of control. You find, wonderful results, and yet they may be spurious, there may be contamination of your material. What comes up will end in the waste paper basket eventually, because your peers will say, look, this is nonsense, we cannot replicate it, etc. So this is where digital humanism comes in, and I think digital humanism is something that can really help us, first of all, to understand that we have to expand the notion of control to cover all these impacts that we see technology has. We can no longer say, you know, it's enough if we go for functional efficiency alone. We have to see what does it do to the environment, to people, to us, and so on. And at the same time, to guard against the illusion of control. Because digital humanism teaches us something like humility. You know, it's not the overconfidence. We are in control, and we can do whatever we want, because this will turn out to be a disaster, and we have enough disasters in the world already. So this is my little contribution to your wonderful topic of the hidden ingredients. Thank you.
Thank you. So, do you want to add something? Sorry, you took some notes.
I was taking notes, but probably Wolfgang wants to.
Yeah.
No, basically, yeah, okay. What Helga just said was so eloquently said that I won't add anything to it. Probably I could develop a little on what Gerti said at the beginning, education, education, education. I might add a question, education in what? And how. I come from a country that prides itself, it's France, that prides itself with being the home of the ingénieur à la française, which is, you know, their way of saying that they train not only scientists and engineers, but also people that have some competencies in humanism. The problem in my own experience is that this model is basically a lot of BS, and that in the best situation as of today, we train people who become, who do humanism as a service, you know, as a service to government companies, and that is a problem in itself. But the alternative is not good either, because the other situation is when we train engineers, or I mean, I teach in an engineering school, so engineers that do a bit of humanism as an assignment when they are student, then they stop for the entire career, and then they do a little bit of humanism when they retire, humanism as gardening, if you want. And now the problem is, again, how can we, apart from education, help to make the contribution of humanism stable all over the career, in each step of the career of a scientist, of an engineer, of any person with a STEM diploma or degree. And this is an open question. It's probably a question for you now, for later, but it's a question that I think it's always important to ask.
Okay, let me just mention one particular aspect of digital humanism, also connecting to what was just said. For me, one important part is to always think, okay, there's the human who wants to use the system, right? Or this is the human where we want to build a system for. And that means, going back to what you had in your history lesson, we first automated systems, so we have to make them safe, right? So they don't hurt somebody. We then invented computers. They have to be reliable because their calculation have to be trusted. Now we are automatic intelligence in some way, right? And intelligence means, or would you like an intelligence which is not moral or ethical? No, right? So this is again what we have to think about. And so related in this, and this is obviously same related to control, right? In all of these ways we want to control because we want to have these systems work for us, with us, right? And that's a really important aspect.
Try to answer, and as I totally agree with you. Yeah, it doesn't make sense to say I make a bit of, I make a course on, let's call it humanism or digital humanism. All the other subjects, forget about it, and then I don't have to touch this topic anymore. This comes back to, you know, what we have already seen over the last at least 30 to 40 years. You know, I think the Faculty of Informatics was one of the first who had a chair, a full professorship in the area of technical assessment, assessment of technical systems. It was already in 85 when it has been established, and they had an own compulsory subject in the, at the time, diploma level, and then at the bachelor level. And what it, in fact, what it caused was they were always the soft guys, yeah? And the hard guys code. They don't take care of the soft issues. And this was really the, excuse me when I put it as bluntly, but this was really the habit over the last 30 years. And all of a sudden, as we don't have this chair anymore, I have to say, the person retired, and we managed not to fill it again in this area. But all of a sudden, we are forced, independently if we are hard or soft or in between, we are forced to really tackle these societal problems. And I think the main reason is that now we are both forced by our by our governments, by society, by what is going on in the world. And we have now regulations in place where even the employer have to look at what are the systems they are building. Regulations like, we start with this AI Act and the Digital Service Act and Digital Market Act and so on. So there is, I would say now, an awareness in the society where we as a researcher and teacher at a university can build upon and say, it is really our responsibility in each and every subject to question what we are doing. This was not the place, this was not in place, as I said, 30 and 40 years ago. Yeah? But I think this is one answer. The second is that we really have this, this is, I think, very, I would almost say practical. Companies have to look at their, at their products in an environmental, societal, governance ways, all these ESGs, all these sustainability goals. And I think they can't, to a certain extent, they can't afford anymore to really ignore these aspects, because I also guess both from their customers, perhaps even from their shareholders, and also from their employees, perhaps there are certain requests now. Huh?
Talking about universities and curricula. Universities, in some respects, are at the forefront of the production of new knowledge. Great sites to produce new knowledge. On the other hand, they have very conservative structures. And the conservatism is partly in the disciplines and the silos, but partly there is this very unfortunate dichotomy. There are the hard sciences and the soft sciences. And this is, in my view, a relic of the 19th century when it started, and where, by the way, the humanities were much higher in status than the technical disciplines, and this only changed in the early 20th century in terms of status. But we still have this kind of dichotomy, and you have to do away with this. This is no longer, the world has changed, we live in a different world today, and the challenge, and this is why I would like to come back and say, you have to challenge also your students. It's about putting control into the technology, but the notion of control needs this vast societal expansion. You have to think of all the possible damages that can be done, the impact that can be done, and some are good, some are bad, but in both cases, you need the technical skills, you need the knowledge to be able to control it, so that the goals that you set, the specifications that you have, can be met. So this is for people who like to play with technical things and like to solve technical problems. It's there, but you have to rephrase the goals and to make it clear this is the world in which we live in, and after all, if we are not looking at what it does to our environment or to our mental health or to the mental health of our children, etc., the world will be a very dire place.
now it works maybe. No, because maybe also, do you want to say something to this? Also, in the context that you were involved in the kind of creation of the guidelines of the UNESCO on ethics in AI?
Yes, certainly. I think the context of the UNESCO ethics actually leads into the discussion that I think you're going to ask me to have around, developing countries. I mean, the idea there, already there were ethical, guidelines about AI being developed within, say, the IEEE and so on at the time. And the question, I was in the group that was sort of looking at whether there should be a recommendation from UNESCO around AI. And the question we had was, what will be the added value of a UNESCO recommendation? And I think the key thinking was that this was going to represent humanity much more broadly. We were going to be, in a sense, talking about what AI might mean for the whole of humanity rather than just for business or for particular groups or particular companies that might be developing AI for particular users. And I think that is the context that I believe we should really have in mind quite strongly, also in digital humanism. And humanism is humanity as a whole, not necessarily just part of humanity that might be using AI directly at the moment. And I think that the important thing here to stress is that we don't really have time to sit back and say, well, in time there will be, we'll need to think about the rest of, as Antonio has already pointed out, the rest of humanity is being impacted in negative ways, potentially. And I think particularly with the potential for disinformation, as the Digital Humanism Chair stresses, that is also a great potential for danger to humanity as a whole, not just our society or Western society or American society, as we've already seen, but humanity as a whole. And I think we need proactively education, actually educating ordinary people about what AI can mean and understanding how they may be being misinformed is something that we need to do urgently, probably, certainly. And I don't think it's an impossible task. I mean, if we think that human beings are actually able to understand another human being, we all have that ability to, whatever it's called, the theory of mind we have. And that enables us to interact with other human beings that are infinitely more complex than AI systems. For sure, we should be able to educate people about what AI systems are doing and potentially can do and the dangers they pose. And I mean not just educated people, I mean ordinary people, people who are just living their lives as ordinary citizens. And I think that the problem is that AI as developed up until now has been deliberately trying to obfuscate its actions and hide what it's doing, hide that it's gaining information from you because, well, the people developing it don't want you to know what's happening because that's part of what they're trying to do is to influence you through their advertisements or whatever they're doing. Maybe they're being benign, but potentially those systems are very open to being misused. And so we need to be thinking about how and regulating how AI should be much more transparent, and this comes back to the transparency point, because if we understand if people can understand what AI is doing, then there's the potential it will be used in a positive way. Sorry, I've spoken too much, but that's just my thought.
Thank you. Does anybody else would like to add something here?
Maybe the audience.
Yes. Steve. No, but maybe first you, and then we will go to the audience.
No, I think we are pretty much in agreement here. It's just how to get it done precisely.
Okay. Are there suggestions from the audience how to get it done? Yeah. But, yeah.
Well, before I give my suggestion on how to get it done, I would like to check with the specialist whether my impression that AI systems that are based on neural nets and deep learning are in principle uncontrollable.
No, I wouldn't agree with that. I mean, we are AI systems that are based on deep networks.
No. I mean, as a technology, are you able to predict the results that an AI system based on deep learning will give? Are you able to ensure accountability, like or explainability? How would it work, considering the technology the way it is, which is influenced by the dynamic process of being trained on a specific text corpus?
So certainly, I think there are many attempts, and some reasonably successful, to attempt to introduce transparency and interpretability into AI systems. Certainly ChatGPT is not one of those, and it is very clear that it's not currently presented. It's not transparent how these things are, but that doesn't mean that can't be done. I am not against saying this technology is at fundament bad and should not be developed.
No, I'm not saying that either. I'm definitely not saying that.
Okay.
The question is, are there any workable attempts at doing it, you know? I mean, I understand ChatGPT is hype, yeah? So it's certainly not what the research stands for. But how would you even do it? To make the system accountable for what, like I've been playing around with ChatGPT, yeah? And amongst other things, I have learned that I died in 2021. The system was sad about
You look
that.
incredibly in good health.
So then I permitted myself to ask from what sources this information was derived. Then I got the answer, were from several reputable media outlets and academic institutions, yeah? So then I said, amazing, I'm alive, I'm Christiane Floyd. Then the system said, oh, Professor Floyd, I'm so glad that you are alive. So the point is, you know, that the system, upon understanding this, in quotes, for the moment, did not memorize it for my next chat, because in my next chat, again, it said, unfortunately deceased in 2021. So are there any attempts at sort of making me in charge of correcting the system's way of learning and knowing if I know that there's an error?
Excuse me, may I just, I don't know, do you know Christiane Floyd? Of course you don't.
He knows now.
You know, and I guess most don't know. Christiane Floyd is the first female computer science professor in the German-speaking part of the world. This is Christiane Floyd. She's still alive. She got her first position in the 70, I'm allowed to say it, in 78 at TU Berlin. She's an honorary professor of our Faculty of Informatics at TU Wien, and she knows what she's talking about.
No, but I'm not an AI specialist, I have to say that, yeah.
I think one way which is being discussed is to give references, right? So ChatGPT as a system just tells you something. Now both Microsoft and Google try to put that into the search engine which comes with these references, right? So as long as I can check these references, right, then I can still believe the references or not. Probably there is actually some reference which says you're dead, right? Which then when I look at it, I say that's nonsense, right? Because we know that there's a lot of nonsense on the web, right? But I think that is one way where we can increase trust or where we can make these systems more useful, right? That it just does not tell you something, but also gives you the kind of justification. I believe this, I said this because I read it there and there and there, right?
But you see, I'm just using myself as an example because I made this experiment with myself, yeah? However, it's not about me. If I find out that there's something wrong being reported by ChatGPT, I cannot do anything because I don't know the text corpus on which it has been trained. There's no author that I can complain to. And there is in principle no possibility of making a suggestion. It's, you know, sometimes they compare it with Wikipedia, which is of course a completely different technology, but in Wikipedia I can write and say I'm in fact alive, yeah, and then they will correct it. But who do I contact in the case of ChatGPT?
That's a good point, right? So my answer did actually not answer this question, yeah, and that's much more difficult, right? Because you're saying, what if I get a wrong result from a search engine, right? And ChatGPT is even more complicated. So changing what it says, that's more difficult, right? I do not yet have a solution for that. Yes, that's a good point.
Juliana, if I, okay.
We don't hear you.
It's not a matter of, oh yeah, good.
So it's definitely more difficult to change a system like that, right? Because in Wikipedia you can simply update the data, but also in ChatGPT we have this thumbs up, thumbs down, this human feedback reinforcement learning systems. And, but it needs some time until it is there. And this is the way how we can update the system, but then we do not have any because it's a stochastic system, we do not know if we also change something else in the system, then maybe another thing is not going right, or...
Yeah, I think that will not work. It will not work. It's the same thing as if somebody else tells you something wrong, right? So it's one thing if this person says, okay, I believe this because I've read it there and there, right? And then if you want to tell this person, no, this is wrong, believe this other thing, he or she might not believe you. It will be the same thing with these chatbots, right? Because they've read so many conflicting things, right? You will not be able to teach them this is right, this is wrong, right? So the most I think you can do is ask them, why do you tell me this, right? Give me the justification, but you will not be able to say this is wrong, right? Because it might give you that justification. I read it there. And then you as a user can only say, okay, I don't believe your reference, right? And so this is why it's important that we ask this question. But for these complex systems, you will not be able to teach. We are not, I mean, right? It's the same in our discussion.
Yeah, but the original question was put to John, you know, are they controllable or not? So, you know, things improve, and in the future there will undoubtedly be also improvements. But if you say it cannot be corrected, is this your final verdict, or do you say we have to work in order so that it can be corrected, is my question.
I don't know.
Well, I mean, yes, I think the answer is the technology is not there yet to correct it. By the way, my age is 10 years younger on ChatGPT, so I'm not so keen to correct it that quickly, but it certainly is not there at the moment, but that doesn't, I mean, it's an active area of research. And I think the problem we have is that a lot of the research in AI has been directed towards the types of systems that we're seeing used in, you know, large companies. And the types of research that are needed, which, you know, the human-centric, let's say, AI agenda, is only being developed within the European context in the last few years. And so this is active area of research, but I don't think we have the systems there yet to do what you're asking, is my answer.
I'm sorry, just to introduce probably an oblique way of saying it, you seem to address the problem of controlling this technology only from a technological point of view. Is it possible technologically? We are not there yet. Okay, I can agree with that. But there are other tools in our toolbox. For instance, we are there yet from the legislation point of view. If you have been following what's been happening with data authorities all over the world, started in Europe, against OpenAI, it was actually about correcting such a false statement. From this point of view, there is unfortunately a very rough and, well, labor-intensive way of correcting this information. And this is basically retraining. And this is what, or moderating the content. This is something that OpenAI does customarily and continually. It does that. This is why, for instance, OpenAI is eager to provide you with fake bio notes, but will never teach you how to produce a bomb, despite my best efforts. And there is also another point, the point that you can ask on which data they are trained. I mean, I've tried, I'm still waiting for their reply, but there is a legal way. I tried just three weeks ago, don't worry, it takes longer than that. But it is possible to actually follow the legal path in order to receive, according to GDPR, unless they don't want to start litigation about that, information as to the data that they use to train, specifically the information ChatGPT provides about the person that requires. I ask not the history of my chat, I don't give a damn, I mean, I can see it, but I ask on which data from Common Crawl they train what ChatGPT produces in terms of actual information or hallucination about me.
Sorry. Yeah, I just wanted to come back to this notion of explainability. It was a question I had after your talk, Wolfgang. And to receive convincing explanations, now, wouldn't it be necessary to combine these models with a symbolic word model, where we have explicit knowledge, which can be used by the system to reason about what it does. I mean, this now sounds a bit vague, but just think about when I see a picture of a lion or a cat, and then you ask me, why did you recognize a cat? Now, then I don't say about the data I use, but I use knowledge I have. Knowledge about mammals, it has 4 legs, but now it sits, so I only see 2 legs. But this is all explicit knowledge I have, and this I use for explaining my reception. So my question is, has this been skipped in your taxonomy because it is so far away it does not work, or is there already something, or would you even agree that this is the way explanation should be given by an AI system, even if it's based on data and machine learning?
I think this kind of explanation or grounding or justification or provenance, right, however we call it, is the only way to make these systems usable or understandable, right? So because then you can look at the reasoning, you can ask, why do you tell me this? And you get an answer, and then you can believe this chain of reasoning or not, right? That's really, really important. Whether and if you ask whether this has to be symbolic or not, I would say probably yes, because when we give this explanation, in many cases we give these kind of rational explanations. As a word of caution, maybe sometimes we cannot, right? Sometimes when I ask you something, why do you do this? You say, I just thought it's the right thing. So it has to be seen how far we can go with symbolic explanations, but I think they're really important.
No, just that I agree. Okay. So another question from the audience.
Please, bitte schön. Bitte schön.
I would like to know your opinion about is economics a poison or is it a spice for what we heard today? I think that the control lies in the big companies which are easily ready for gain to just to ignore humanism, just to employ people for $2 a day, and all this would, in the end, control what will happen in the future with AI, for example, and this might not be the direction we want to see.
I think especially in this, if I may answer, especially now in this context of large language models, right, which are in the news all the time now, we do see an encouraging movement towards more open source models, both in the academia and both in kind of other circles, right? So the really bad thing with GPT-4 is that we don't know exactly where this trained, how big it is, what exactly it does, right? But we see that there are a lot of research groups which work on somewhat smaller but still very, very powerful models which can be explained. And there's this, I'm not sure if you have seen it, this interesting letter from a Google employee, which is obviously not the official opinion of Google, right, which says, okay, both we as Google and OpenAI as OpenAI, we are not the only ones who can do these models. If this thing goes open source, it has already gone open source, we lose, right? And so that's kind of the encouraging thing that now that it is actually spreading into a lot of groups and there's a lot of experimentation and many of these groups experimenting on more open data sets, algorithms, right, etc., training protocols that will to some extent counteract any, well, let's say counteract to some extent at least the black box danger of these models, right? Okay, that's just one point.
Yeah, if I can make a complementary point, let's say, is that if we look at the, I don't know if the economy is poison, but I know that it's changing the game. If you look Stampfer's Index of AI report that is published every year since 2017, this is the first year, 2023, where the major advances in AI have been happening in the corporate world and not in the university world. So this already is a change. Other important indicators, in my opinion, are the fact that if we look at computing power, even universities depend from Google and Amazon and Microsoft, of course, yes. So, and to say nothing about the data. According to recent inquiries, the main 7 databases that are used for machine learning are owned by, the main data sets that are used for machine learning are owned by 7 corporations and institutions. The corporations are IBM, Microsoft, Amazon, Meta, but then you have Tsinghua University, Princeton, and Stanford. But these 3 universities only have these databases in the framework of industrial partnerships with other corporations. So this is also a matter of saying that there is a stronger interdependency between the academic world and the corporate world. If you go to new RIPS, well, in the last few years, it's basically having, you know, keynotes from Google and Microsoft who just do their laundry list. They say what they want from you to research and just do it. Yeah, this is something that is changing the game to a large extent.
Yes, hi. So I found a question very interesting about control and if control is entirely possible. But I'd like to introduce like a temporal dimension to that question, because in fact I think it's not important whether we can gain control or not, but if we can gain control fast enough before this technology, you know, exterminates us all. A question to the round, of course, do you think it is possible fast enough? Because when we look at issues like climate change, of course, we have a technology that has been around for a long time, and obviously we have not gained so much control over it that we have control over how much CO2 is emitted and so on. So obviously we have not gained control over that technology fast enough. Or the question is if we will be able to be fast enough to stop climate change, and the same as with machine learning technologies, are we able to gain control fast enough to mitigate or stop disaster from happening, basically. So obviously nobody can look into the future, so it's more of an opinion question, but I'd be interested what you think about the question framed this way.
Maybe just one comment on that. I don't see the technology in itself as taking the control. It's bad actors using the technology to take control. And I think on that count, yeah, the jury's out. I don't know. I mean, I think that we need, as I said, to think about how to educate people in terms of understanding. We certainly need to think about the, promotion of ethical principles. And, the UNESCO one, I think, is a great example, and it was signed up to by all the member states of UNESCO, including actors you would not expect to sign up to such a thing. And it includes provisions about, the correct use of AI, the, non-invasive, non-controlling, etc. So, in principle, people have agreed that that's the right way to go, but then... Exactly. But the question then is implementation, and I think this is, something we all have to just work to try to support. And the other thing, I was going to say in terms of the sort of more global dimension of AI, I think the danger is also that it's seen as another way in which, the developed countries are stepping ahead of the developing countries, and in some sense alienating them, and they're feeling even more kind of left out. Climate change is badly affecting them, they're left out of AI, they're being paid $2 an hour to do the grunt work. But I think there is an opportunity to engage with them positively in helping them use AI to tackle challenges that they have, or we all have, in global, in the Sustainable Development Goals, and to essentially also make the assessment of our progress more objective and transparent. And I think that, it is an opportunity, because it is a technology you can use remotely, it's actually an opportunity for countries to leapfrog forward. And we've certainly had very good experiences in working with African researchers and projects, seeing people really excited and engaging with using AI in challenges that are relevant to them, developing data sets, etc. So I think there are positive spring roots, as it were, but I certainly wouldn't want to make a prediction on your question.
Okay, so just so that we don't all agree, I think the analogy between climate change and AI is really very wrong, because climate change is something which happens because we don't change our lives, and that has a lot of reasons, right? Economy being one, or whatever, right? So there are many aspects, right? So we know what we should do, but we don't do it. With these AI advancements right now, there are actually a lot of groups. Yes, there is OpenAI, which builds this black box, right, which is bad, and we are afraid that this AI is used in some bad ways. But there are many groups, both in research and in civil society, which work on on more open models, on explainable algorithms. There are all these discussions which we also have, right? So I think the situation is really very different, and there are many more actors now in this context. I mean, you are right that obviously computing power is a problem. I think it will not be a problem anymore in 2 or 3 years because the models are becoming smaller, right? And so we have many more opinions and many more drivers, even though right now it appears to some extent it's true, right? So, I mean, of course you have a great computing and research environment, Google, right? But there are many more other drivers and groups who are there to kind of stand and work for other goals and make this more trustworthy, let's call it.
If I may, I don't know, this is very true, Wolfgang, provided that the question about the relationship between AI and climate change was in terms of a metaphor. Was it a metaphor, or you were actually talking about the impact, the sustainability and durability of the development of AI?
So, sorry. So why I used it as a metaphor? Yeah. So in my mind, there's a technology that is super useful to humanity, but it has negative side effects. All right, that could be,
for instance, in terms of carbon in
the diesel motor and machine learning. Yeah. And in both cases, basically, we had this technology invented and is widely used. And the negative side effects came to be known later, at a later point, or maybe become known immediately because some were unsafe and exploded or somewhat. But yeah, so we have that hugely beneficial technology that is used worldwide to great effect, but it has negative side effects, and we basically have to all agree to not use that bad version of the technology anymore in order to not destroy ourselves. That's the peril that I see.
Okay.
Yeah.
Let me reframe it. What if it was not an analogy? What it was not if it was not a parallel, but we were talking of the actual impact in terms of carbon print and the consumption of rare earth and raw materials when it comes to these technologies? Because this is an actual problem, and a problem that has been underestimated over the last few years. Only recently, people are starting to think about how much energy we consume every time we train a model, and unfortunately, only in the training part. We are not thinking about all the other phases. And this is probably something that, I mean, frustratingly so for me, because I've been trying to start and fund a research about this for a number of years now, and nobody wants to give me money to explore all the mines of lithium and cobalt in the world. Who knows why? But anyway, this is something that, in my opinion, is an actual question. And how do we gain control fast enough? That was the question. In my opinion, if we gain awareness fast enough, if we study these topics quickly, as soon as possible, and then we start asking the question, not asking the question in a vague and abstract way.
Thank you.
So I think that then we will soon come to an end, but I would have a question for you for your talk today, because you were characterizing the situation, and we mentioned it now also with this human labor, but what is the perspective, so to say? In the end, you said we cannot get rid of the situation, that we need the data, but is there some positive conclusion or something that we can do?
Okay, let's say the jury's out about what's going to happen with these so-called low-skilled data work. My money is on it will increase and become even more pervasive. In some cases, it will be underpaid. In some cases, it will be entirely unpaid, as it is already the case with all the free labor that we ourselves as users who train or retrain or verify or reinforce models already provide. But there is, of course, a way out, a path to escape this situation, and unfortunately it's not a linear one, and it's always been the solution in terms of struggles for the recognition of rights of those who produce this labor and who provide this labor. And there are some initiatives that are already have already started in this domain. These are, let's say, following the wave of other struggles and for the rights of workers, specifically platform workers, like you have seen for Foodora, Deliveroo, and of course Uber. This started as something that has nothing to do with data work, but now it's percolating, it's transferred into the micro work, data work, crowdsourcing, crowd work environment. And in a few weeks I will be in Brussels to discuss with a European Union a new initiative. There are legal solutions that are advanced in France and in Spain. There are a number of class actions that have been going on around the world, meaning groups of data workers that come together. In some cases they unionize, like recently in Nairobi. They were people who did the training or the moderation actually for ChatGPT. They are now in a union. And in other cases, they have been successfully challenging these companies for economic and in some cases ethical reasons in France, in Brazil, and new and exciting actions such as initiatives such as these are flourishing, luckily.
Thank you, very interesting. Yeah.
I'm sorry. I'm sorry, here. Maybe you're already doing the conclusion, I'm not sure. I just have one quick question, but I think can also be addressed for everyone and can also help everyone. So there's an open letter circulating around for a few weeks now that asks for research groups in industry, but also in universities that work on systems that can no longer be distinguished from humans, so they pass the Turing test, that the development on these systems should be stopped for 6 months. Most famously, this letter was signed by Elon Musk and Joshua Bengio.
Who immediately created a company that is developing.
He created OpenAI, but when he created OpenAI, it was actually still open.
He created a new company soon after.
But now OpenAI is no longer open. Yeah, but anyway, have you heard of this letter? Do you think it's a good attempt? Do you think it does any impact on stopping some groups for working on 6 months? Do you even think the Turing test is still appropriate on judging these systems? So, yeah.
No, she just created a new company where he
sorry,
wants to train a new model.
Let's do it the following way. Let's make a round, yes, a final round, because people are already leaving now, and I think, so where you can address also this question, and maybe more broadly even, because, I mean, we are here at the Technical University, many are computer science students, and it's really hard for us to judge these things, and also what is happening right now and the impact, and then between, I do not know, these Duma perspectives and yeah, nothing special. So how should we also maybe deal with this uncertainty of people? I mean, how to communicate to the public also these issues. I mean, when we as an expert are even not sure or not one. So to extend a bit, because this letter had, of course, also a broad public reception. So yeah, and then yeah, I would make this as a final round now.
Do I start? Okay. As a general rule in my career, I have one simple principle: never sign something that has been signed by Elon Musk. Simple as that. Having said that, I am not sure, despite the fact that many remarkable colleagues have signed it, I'm not sure that a moratorium is the right way to go. moratorium, meaning we stop for 6 months. Why do we stop? Why for 6 months? And what happens during these 6 months? So a number of questions that are open, and importantly, we have always to think to remember that these open letters do not happen in a void. The open letter is the new version of another open letter that was published in 2015 on the same platform, largely by the same persons. That was the open letter for robust AI, which kick-started the fad of the ethical AI. I see some of my students here that have attended my class on the ethics of AI, and they know all the bad things they have said about that letter back in 2015. Now, 8 years afterwards, we are back at square one, exactly asking the same thing and obsessing about the same kind of imaginary dangers, like robots coming from space and colonizing our breakfast, I don't know, whatever.
Okay, I like to go back to how Gerti started today, which is education, and maybe I'll just stress one aspect which I think is crucially important for everybody. Try to understand the technology or try to understand whatever, right? So I'm sometimes surprised that school teachers or students do not want to understand, right? They are kind of happy to leave this as a black box, and then they discuss it on a high level, right? Sometimes we even do that. Sometimes maybe it's necessary to focus on the high concepts and principles. I do agree with that, but I think especially we as researchers, right, we have the responsibility to first try to understand ourselves, right? We don't understand everything, but we try and we become better and then help others understand as well. And therefore the only way to kind of get some control over what is happening, right, is understand the thing, right? Otherwise, and if you say it's a black box, right, forbid it, it will not work. There will always be somebody who will use it, and then I don't understand what he's doing, right? So it makes no sense.
It's difficult. When we look back in the history of science, you know, there was the atom bomb, and there were certain physics scientists who said, okay, when they realized what they have kind of explored, they wanted to stop it, and it didn't work, and the atom bomb was built. When we go to genetics, and there's this question of, you know, should we do, you know, intelligent design in the sense of changing, you know, the genome of humans? There was the decision that we shouldn't clone, and it has been done already. But nevertheless, there is still a certain, at least what we know, a certain understanding that certain things on the genetic, as on the genome level and molecular biology level shouldn't be done. Now we are in computer science, as in the AI area. Concerning this letter from Elon Musk, I mean, this, of course, don't trust Elon Musk. Yeah? I think we can't stop the development, the technological development. What we should stop are certain applications. I was mentioning these autonomous weapon systems, lethal autonomous weapon systems. We should, I think, generally stop using technical AI-based systems just as a black box for applications which really may harm humans. Yeah? This is also in the health area. It's also, I think, in the education area. So here, I think we are we are on the forefront as scientists, as responsible scientists and societies, that we really develop here the right ethical, value-based behavior. But we never, I think, stop technical development. This, I don't see how this would work.
Yeah, so I guess I'm going to agree mainly. I mean, I think we've been actually incredibly fortunate that this has happened in a company that has made it publicly available. It's actually given humanity a view of what AI can do. That imagine it had been developed in, a private lab or a research lab for the military in some other country, whichever country, and its potential misuse. And that would be so much more effective if we hadn't actually seen it working as we have with Element AI. To stop the production at this stage would just give those labs a chance to catch up without us seeing what the next step is. And to some extent, I think the next step is potentially, the technology. We have to think about how to use these technologies to help defend against the technologies. In a sense, that's happened with fairness. We now have ways of measuring fairness that have only been thought about because of the misuse, if you like, of AI, or the fact that AI has been biased. That has given us a whole new insight into how we might measure fairness and how we might assess AI systems. So I think we have to go with the punches, as it were, and learn to be one step ahead if we possibly can. And if we do, maybe we'll make it. As your question asked.
And thank you to the panelists, thank you to the audience, and I think it was a very, interesting and insightful afternoon, and our panel discussion with a specific dynamic, but interesting, I hope. And I do not know whether one of the CAIML directors wants to conclude. Otherwise, no. Otherwise,
Also, thank you for being here. Thanks to all the speakers and panelists. Also, thanks to all the colleagues who chaired the session, and special thanks for Julia for chairing the panel. Thanks. And as usual, many thanks to the technicians in the background.